Okay, so today we're going to talk about ADIOS and specifically ADIOS II. So the first thing is I want to thank my hosts for inviting us here. It's the first tutorial that we gave overseas since the pandemic. And the whole thing is we were supposed to come essentially the week of when the pandemic started, we were supposed to be here. So it took a few years, and we've had several versions of ADIOS since then. So one of the things that you'll notice is that ADIOS has a lot of developers, a lot of contributors. I mean, there's actually a lot more than this in the ADIOS contributors. So essentially, we started out as a research project and moved forward into a production system many years ago. And with ADIOS II, the final thing I'll say on this slide is when the Exascale computing projects started, what happened was the US had this initiative. We wanted to be the first ones in the world, if we forget China, but the first ones in the world that would have not just an Exascale computer, but to have applications ready. And the point was, it's not just the applications alone, but the applications actually use libraries such as ADIOS. So there was billions of dollars invested, not just in the hardware itself, but it was invested in the software technologies. This started roughly 7 years ago. It's going to end September 30th of next year, which is the end of our fiscal year. And ADIOS was completely rewritten at that time. So you can imagine what you're saying, every line of code we're going to throw away. It was all in C, essentially, and we were going to write it in C++. And what we're going to do is use the algorithms. And then we're going to keep designing further, mostly based at the time on the Exascale computing project applications. I'm one of the co-PIs of the Fusion application. It's what we call a KPP1. I think there's 5 KPP1s. I might be off, there might be 4 or 5, but that's key performance something, sorry. But the goal was, could we get the applications up and ready, and could we get them 50 times faster? And ADIOS was an essential technology for the Fusion application. I'll describe that in a second. So I talked yesterday, probably not everyone was there yesterday when I was talking, I really don't know. And one of the things that ADIOS was set for was the problem of storage and the problem of storage falling behind with computing power. A lot of that deals with the cost, meaning you could make storage systems to be extremely fast, just more concurrency. It's hard to scale certain things, and that's why you see file systems, they get harder and harder as they get larger and larger. And in Oak Ridge, we have something that's large, but again, not everyone can get the performance, and that's where ADIOS is for. Let me just move forward. I explained this yesterday. This was my life in supercomputing, and this was in my graduate school. And the thing I keep saying is, imagine at that time a 2.7 gigaflop processor, which was the state of the art. I know that seems nothing today, but back then it was good. It was a vector architecture. Vector, of course, similar to GPUs nowadays, but it had an SSD for storage. So that was something really tremendous because we had so many bytes per, bytes to disk per operation. But this is our latest system. It's similar to Photonics. It's all GPU enabled every node. I mean, it's the same basic system, right? Just larger. It's going through acceptance right now. The acceptance is supposed to end, in a few months. And, the file system is supposed to be one of the most state-of-the-art. It's Lustre for the main storage. There's 300, Norbert, 300 and how much petabytes of storage?
250,
What?
200.
250 petabytes of storage, which is quite a lot. But the problem with that, of course, is you fill it up. And one of our goals for ADIOS was to allow applications to fill it up really cheaply to annoy all the system operators. But it was really to say, write your valuable information there so that then you can do other things with it. Don't get limited by that storage. So in all this, the point is that we do have also this burst buffer storage. There's separate NVMe on every node. You can use it. We've had that on our current system Summit. And I asked this the other day, I'll ask it here, like, how many users on OLCF, the Oak Ridge Leadership Class Facility, use the burst buffer storage for real runs? How many do you think? Hundreds? Thousands?
Percentage? 5%.
No, we're not that high. I mean, maybe there's like one user that ran with it. And it was, when you write to it, what happens to it? Well, after the end of your job, it's gone. All right, so I'll let Norbert continue. So the point is, we've gone a long way.
How do you get rid of the tunnel?
You can minimize this, pull it.
Minimize.
All right, a technical. Like me. Just use the
It's viewing okay from this side.
And
That one or the other.
So when we talk about ADIOS, how was ADIOS created and what was it created for? I try to say like, this was one of the first papers that I was on. This was about binary black hole coalescence. And this was trying to actually create what we call the initial value studies. So relative, you have an initial value problem. And we had to create the initial value problem. We had 3 different ways of doing this. Well, one of the things that when I was actually a student, we're running on that cray that I mentioned. And it's like, we needed to see results quickly. So the first thing that I learned as a student was, you wanted to have a way to quickly see on your screen. And at that time, we had these SGIs. They were, again, the visualization machines. And we're getting quick visualizations into our numerical algorithms so we can adjust to get our algorithms to be stable. So what we learned, or, and what was the part of ADIOS there was, you wanted to have this IO componentization, whether it goes for visualization or whether it goes to storage. Years later, that was here. That's where, okay, what happened? So back in 2000, I went to the Princeton Plasma Physics Lab. It's a Department of Energy lab. It's one of the largest fusion labs. And one of the things is that I was working with a researcher, Zihong Lin, who actually had in science code, and we were looking at zonal flows and the effect of zonal flows in fusion, in fusion reactors. And if you know about zonal flows, like on the sun, it's like how turbulence moves across. It's how energy comes out. So this is a very important process for fusion. We were actually running back in 99, 2000 on an IBM SP, and we were running at that time off of 1,000 processors. And of course, the processor was a node at that time. So we were running at that time, and back in 2000, we were trying to write out to get the science information, 1 terabyte of data in a day. Now, that doesn't sound like much today, but back in those days, it was like heroic effort. And the thing that we found, and again, this is just copy a little bit from the supercomputing paper, and the thing that we found out was that the time it was taking to do parallel IO, and we tried 2 ways, HDF5, and then we tried another thing, MPI-IO, which was part of it. it was taking 65% of our time. And you can't write out a terabyte of data with 65% of your CPU time. So you just don't write much. It's an easy thing. So what we had to do is something better because we couldn't get all the physics out. So we came up with this algorithm, which basically came out with this file format, which was called BinPAC. So today you'll hear about us talk BP5. BP originally was BinPAC. So it just came from here. But the other part of this was that we tried to do is that it wasn't just writing asynchronously. It wasn't actually new to its file format. It was actually moved in the data from California over to Princeton, which is, I guess, a little further than Sydney to Perth. So we were actually moving it, visualizing it, and trying to understand what was happening during the calculation to control it. So these were the beginning days of ADIOS. And it was all about these principles, really fast I/O, about can I just switch from seeing things, visualizing it, or to go over and having it to storage, and then having ways that could work either wide area network or local area network. So all the things that we're going to talk about were based upon this. So I feel old when I talk about it, even though when I talk about it, like 1,000 processors for some people today seem large. And I'm like, well, that was like 2000. I mean, that was a long time ago. So, you know, I'm kind of immune to so many things. A terabyte small, that was large back in 2000, but today that shouldn't be large. So let me just go further. So ADIOS, we're going to talk a lot about it. It's an I/O componentization. It's, as I said, ability to do in situ and do different ways of in situ. Whether you want the application running, in situ then can mean ParaView, Catalyst. It just connects and the application stops and they're on the same node. It's going to then visualize the data, or it goes to different nodes, or it goes over to wide area network or local area network, different nodes sharing cores in the same node. Just a set of abstraction that you can do all of it without changing your code. And then there's the format. And I always talk about it's a string, it's a self-describing format. So the thing I've given a lot of talks is for any researcher who doesn't use I/O middleware, such as ADIOS or HDF5 or NetCDF, or then what you're doing is you're writing your data out such that almost no one can read it. What I mean by that is I know how many physics codes work. There's students, there's postdocs, they write some extra things in there. If it's a pure binary format, reading it becomes impossible 5 years later. It's like, oh, well, I don't know where the student went, so no, we can't read it anymore. Because, you know, it's binary. There's not self-describing, so you need self-describing data. And the reason why a lot of people weren't using it was for speed. So what we tried to do is say, well, how do we give you high performance, at scale, self-describing data? So that's really ADIOS. And there's a lot of other aspects of ADIOS. We say it's a declarative self-describe API, and it's separated by the I/O strategy. And again, what we mean by that is you're going to put data, how much concurrency, how that data gets aggregated, how it gets to storage. Why should I'll call most users physicists, not to sound bad, but why should scientists who are non-computer science, non-experts, try to say, oh, this should be merged together and look like a contiguous piece on storage? You have to say, what does that even mean in parallel storage? So, and what I mean by that is, you know, you guys probably know Lustre a little bit, correct? Like, who doesn't know anything about Lustre? Well, remotely, no one raises their hand that I can see. So again, what the abstractions that our community gave for parallel I/O, what they tried to give is they tried to make, say, Lustre look like one big disk. Now, if you think of the early days of parallel computing, if I made your thousands of processors look like one processor, and that was the old SGI days. Do you think you can get high performance at scale? You always worry about concurrency, right? Locality. You always worry about these things. Okay. You go, A, this is just insensitive, or B, my fingers too close to. So what I'm trying to say, so a lot of what we do is we try to do things like avoiding latency of small writes, buffering data. So ADIOS has this unique thing called step. And we'll talk about a step. And if Norbert hears me say, think of it like a time step, he always yells at me. So I won't say that.
Try not to think of it as a time step, okay? And it's not a pink elephant.
So what I'm trying to say is, and again, please ask me any questions. Ask us questions. This is supposed to be interactive. These talks are no fun if you're just lecturing. So ask questions, please. So what we tried to do is we tried to do things like in Muster, there's a thing called lock contention. So basically, you don't want two processes writing to say, to the same OST, which is the object storage target. So you want to be really careful about things. So ADIOS just kind of does things away from the user because the user never specifies it. So that's what ADIOS does really well. It does things like, it writes subfiles. So I've always asked people, like when you're on a Lustre system, if you're writing from say 10,000 processes, okay, so we'll call them 10,000 nodes. How many files should you write if you want to get high performance? Or guess.
File every underscore.
I would say it's an ill-posed question. Because the thing that you should ask back is, well, how many storage targets do you have? And I mean, that's the thing, that the number of files should be proportional to that. What factor? It depends. How large is it? How balanced is it? There's all these different questions. It gets really complicated really quickly. So what we tried to do is hide this from the user. And we'll talk about applications, or I'll talk. This is SpecFEM 3D. Did anyone hear about that code? It's one of the SpecFEM is one of the largest codes around the world for global tomography. Okay, and this is the 3D version. It's written by Jerome Trump at Princeton University, but it's a global tomography code. And if you think of earthquakes or seismology, it's all there. So their code, 2 terabytes per second on Summit. They write a lot of data. I'll have a slide of it. But what you'll see is it's so much data. And what we need for these codes, GTC, there's a fusion code at most HPC facilities. This is like one of the benchmark codes now. And if you remember, I mentioned the early days of ADIOS, this code on 1000 SP, IBM SP processors, that was GTC. XGC is this fusion edge code. That's the main code for this WDM application. LAMPS, that's a MD code. They're all getting over a terabyte per second for realistic runs. So that's really good. But one of the other things, and again, these are things to most, I would say, scientists, all this stuff should make a lot of sense. And all of this should say, why isn't that in every IO library? Well, that's not my problem. But for reading, one of the most common things that I forget who we were talking in the room, but if I had a 3D array that you were writing out and it was distributed across lots of processors, we've always said, when most scientists want to read that 3D array, most people want to take a slice. And the problem is, what the community was trying to tell you is make it this logically contiguous. If I take a slice one way, you'll notice that it's fast. And in this case, it's the JK slice. But the speed with the IJ slice, and again, in a logarithmic graph, you can see it's a tremendous drop. It's roughly 100 times worse in this case. And the thought was, what if you just use a space phone curve? If you add luster, now what you can do is you can just lay things out in this linear fashion across 3D space. And that's that Hilbert curve being shown. And now we can avoid all that. Now you can make it so that you can have fast access, whatever plane you want. Now again, this is kind of driving crazy. Okay, this is something very easy to do. I know Norbert's getting nervous with the time, but the point is, we took that, which was some years ago, and then we started seeing this is another ECP KPP1 code called WarpX. It's an adaptive message refinement code. It's an accelerator code. And like there's a variant of this team we also worked with on a Gordon Bell Prize, pick on GPU. So these are particle and cell codes. And in this case, you know, they have their IO system called OpenPMD, and that writes directly with ADIOS. And if someone can monitor in the chat in case there are questions, because I can't from here. So,
Yep, we're monitoring.
okay, excellent. So the point here is like to get read performance. The other thing that seems to be the problem for today is when you're reading, what I find is scientists write at scale, but when they read, the first thing they do is they open up like a Python notebook. They use Python. That's what we see. And what they do is they slice their data. And now the thing is, what's very unfortunate is that most people, when they run Python and they hit their open, who doesn't have a multi-core processor? But most people use IO that's not actually threaded. And they just think, I need to have the fastest, and that's, I don't even know, the graph on the lower left. Can't see, I don't know, can people see me pointing? I'm in the room, yes, but remotely, I don't know, let's assume. But what happens is that if you have something logic contiguous, this is where you get really great performance. But I always say, well, that's silly. Why would you not use all your cores for reading? You can get faster, better. And what we find is that the file format in ADIOS and in the yellow boxes, that's one node on Summit. And you start to see that in general, that the fastest is not logic contiguous. It's actually the stuff that we're trying to do in ADIOS, which is like either the pink, the blue, or the green. So those are the three different ADIOS waves. So the point is like, because of what you're trying to do is read it with more concurrency, you want these different chunks out. And we'll describe that later, of how that's done. This is a query. ADIOS has the ability to query. We'll talk about that later. This is just talking about variability. And one of the things that we do not have, but we talk ADIOS being a componentization, we've had all the research for the last 14 years on variability at scale with IO. We understand variability to an extent of how the cause is. The graph on the upper right, this is just showing the different days of the week. This was writing the same amount of data to different storage targets on Lustre. And on a quiet day, you would expect actually a sharp peak on the left. And what you find is that some days are really bad. So we can actually integrate this into ADIOS. The reason why we did is after we did all the research, develop an algorithm to handle this, then all of a sudden we had GPFS, and it was like there was no motivation for us because you can't do any of this on GPFS. What we did, which was this.
Scott, we do have a question in the chat at some point.
Okay, so let me first get the question in the room. This one, so this is latency.
I see. So
the latency. Right. You want the latency, the time it takes to write it to be about the same and to be as really, as you said, as low as possible. Okay.
So do you know what happened there? Just
Any physical
in the
example?
different days of the week.
What did cause?
So no one can give you an exact answer. But what I've seen is that, like at Oak Ridge, people are doing a lot more debugging jobs in the middle of the week. The bugging jobs, they tend to write and they tend to read, and people tend to do more visualization and recap it. Okay, and there was another question, if you can read it out loud.
Yep, I will do. It says, are you also using the Hilbert curves to place the data chunks in memory across the nodes in order to avoid unnecessary access patterns across nodes / NUMA banks?
The answer is no. And as I said, we're not officially actually using Hilbert curves today in ADIOS. It's something that I would like to get in the future. So when I talk about having these different engines, so the reason again to do that was not so much about contention, but if I go into this, which think of this as similar, but this is about variability, we developed this rerouting system. Now we worry about contention. So this was saying, for the variability issue, how do we do this? And the basic thing is, if you think of, you're writing from all these processes, that's the SC0, SC3, ... And now what you're doing, you're saying, I'm just going to get these different initial banks. Everyone's going to get a certain amount of, say, processes that it's going to control. So these are going to go onto certain storage devices. These will go on other storage devices, and then we'll have separate files. But by having a global coordinator, the whole part of rerouting is to say, well, everyone's going to get 2 initially, so everyone writes 2. And when you're done, you're going to just have another one sent. And I hope that makes sense then why 2. You always want to be busy, always. And now what happens is when something's slow because of variability, now what happens is one of these is going to finish faster than all the rest. Once you're finished, now the question is, can I ask the global coordinator, or it's not really asked, they're going to know right before I'm finished, and they're going to take some of the other work and direct it to me, which is going to direct it to the other storage device. This creates imbalances, and basically that was the thing. But in the graphs, this is looking at 2 different machines, and you can see it's dated. This was the machine before Summit called Titan. This was Hopper machine at NERSC, the 2 DOE machines. And you can see the blue has much less variability than the white. And again, the I/O time is significantly less. So rerouting absolutely helps, and we know that in networking. So we don't need space filling curves. But then there's interesting things about the imbalance, and then where do you place things, and then do you do space filling curves? But that's really research in our field, so we're not going to discuss. So obviously, okay, there we go. Okay, so this is from the ECP. These again are these are 3 KPP1s. They all run with ADIOS. They've been presented by their scientists, not us. And what you can see is we can reduce the time. In this case, it's looking at XGC for checkpoint restarts. The other thing was writing out the probability distribution function. That tends to be quite large. It's about a terabyte being produced every 60 seconds. So I guess it's not SKA large, but it is quite large. And this is just showing, the time and how fast we can do these things. Again, 13 seconds on 1,000 processors. We want to reduce that further, and we have reduced it further. In E3SM, this was actually comparing what was their state-of-the-art system for Perl and CDF. This was one of the E3SM graphs. You can search for E3SM ADIOS. We'll show these types of graphs. And you can see the time it takes to write is so much faster. And Warpx again. Never changes fonts or not black fonts, so you can't see what that is. But again, it was a significant improvement. And actually what we did, which is not shown here, is this is using Amrex, AMREX. Does anyone hear of that? So they have their own IO. I think it's called plot files. Okay, and what they found out was ADIOS is a lot faster. So, we have another new collaboration, Hypersonics, which is running Amrex. So a lot of the Amrex users are asking ADIOS to be fully integrated as a first-class citizen rather than external library. So one of the things, yesterday when Norbert was not listening to me, unfortunately,
During his presentation, just I always listen to him on his presentation.
he says his boss forced him to do something, and his boss then didn't want to listen to me. But basically the thing was that, when you say ADIOS, I don't remember the exact year that I was first asked to come here. It was before IDEC became Pawsey. So I don't remember the exact year, but Andreas Wishnet, he asked me to come. They had some major IO problems. He had a PhD student, Jason Wong, and they wanted him to investigate ADIOS because they did some initial study. And eventually Jason got his PhD, he worked for me, and today is his last day, and now he's moving back to China. But the thing is, working with SPA, we had a Gordon Bell nomination, and we can just show it's really reliable and really good performance. And, we do always need to go further, but we've had a lot of users, and we have users running at scale.
Once again, the previous slide.
The previous slide.
So these experiments where you show performance improvements, is generic tests or are these tests specifically tuned for particular kind of operations?
Okay, I call that an all posed question. So these are, it's all posed, and which is okay. These are actually for instance, so XGC, I know really well because I'm one of the creators. Okay, so XGC is one of the largest fusion codes in the world, and it's the only code that gets by the edge. The thing is, if you want to understand the kinetics, which is again, think of the particles, you can't write all the particles because that's crazy. Okay, then we're talking about in a day hundreds of petabytes on runs today, and you just cannot. So we compute these PDFs to understand the physics. And all we're trying to do is output it. This is no test. In E3SM, this was a test. That was their test that they run, and they report the results back to us. In Warpx, this is their code running at scale. Okay, so all of our numbers are not from us. And we have all these videos, and again, we can easily share because they're on that laptop. And we have videos from all different scientists where they're talking about what ADIOS helped them enable. I do not ever running a benchmark case and say, oh, wow, that helped.
Right.
It's real runs.
They were able to use ADIOS to speed up their work. Yeah.
Yes.
Okay.
And the real thing in all these cases that we're speeding up is the writing time. That's what's being shown. Now, the question is, why do I talk so much about writing? Okay. So why do I talk writing in these cases?
Well, so in this case, I mean, it's going from 360 seconds to 30 seconds. That's a big, that's a huge amount of time spent just writing. So you wouldn't be able to do it assistance.
Well, think of it in a simple sense. If I think of Frontier, let's just approximate the cost of $1 million US per day if you're running at scale. And these guys, well, these two are running at scale. These guys don't run at scale. But if it's $1 million a day, this is going to write every 60 seconds. That's essentially a computational step that's on Summit. Frontier will be a little faster. And if I'm saving, and that number will go lower, much lower. Now we're showing it about 2 seconds. If I'm saving roughly 300 seconds, in other words, just think 300 seconds. And is that going to matter? And I'm trying to do this every 60 seconds. So I have, that's a minute.
Yeah.
There's 60 minutes an hour, 24 hours. How much money will that equate to? You'll never get the computer time again, meaning if you're going to do something really inefficient for SKA, right? Will people care? If you can't move data, if you have 2 ways to do things, one way is 100 times faster than the other, and you can't, you're not going to do this thing slower because then it impedes your science. And in this case, you only get a certain amount. I don't know about photonics. Like, do you get infinite computer time on photonics? Right? I mean, so you're limited by your run, so you have to think very carefully about what scientific campaign, what you write, how you write it. So if you can eliminate that, then you can get more science done. And that's what this really is. And that's certainly on these 2 cases. So anyway, with ADIOS, the point is there's a lot of things that we do that we've been doing to work so that we can really speed up the writing. And then again, we can speed up the reading at scale. And that's the caveat. If you're only going to read in from one core, ADIOS is going to probably hurt you. But if you're doing that, let's just say, I don't understand why in today's age. But again, there's legacy, and we get that. So we're trying to change away from legacy. The other thing that, again, we're going to say over and over again, this concept of a step. And the concept I try to say is similar to this. You have something and you're trying to say, okay, I need to read in pressure, temperature, entropy, 3 components of velocity. If you're going to program that, you're going to say, read temperature, read. And when you program it, you don't really care if it read one thing before the other. You care that in that certain amount of time, when then you're going to do computation, now you have that data in memory. ADIOS has a concept of steps so that we can do the read whatever order we want. We'll do what we think is best. Because how do you know how those bytes are arranged on that large storage system? So there's things that we can do. The other thing is that avoids all these small little reads and writes.
Are there any assumptions about where we intend to put the data on, like the file system for ADIOS to work the best? I mean, are we always talking about Lustre or Lustre-like system?
I mean, Summit is GPFS. So the systems that we currently have really optimized, okay, are Lustre and GPFS. Now, we've tried many other systems, including, we have a Windows machine and we could time things on a Windows, the WSDL. We could time, Linux systems. So what I'm saying is these are more general principles. What I don't know, and that's something, again, with a partnership with Seth, I just don't know. But no one really does, and no one really knows at scale. And that's something, but I guess my point just comes from basic principles of parallel programming. So I'm like, we've learned a lot. I think all that should be the same, but it's hard to say because systems are designed like on GPFS, like Summit. We can scream with the IO, but the thing, if you want to crash the system, just do have an AI workload that opens up I don't know, 10,000 files at once. See what happens. And then do that many times, and you'll get messages from system admins telling you just crashed the system. Fix your code and tell us when you're done so you can run again. And you will get that. And initially, a lot of the early days, like I mentioned this global tomography code, They came to us because they can't run until they fix the IO, because they were using a format called seg-y, if you know seg-y. That's the industrial standard. That's what they use in all the companies. We did all the stuff with BP, the company. So BP was using the BP format to help a lot about that, moving away from seg-y. Just go further again. So the thing is, the other, so one of the big pushes that we try to say, and I hope this one makes sense. You know, I think of things, again, going to like the physics, like what's happening in Mother Nature, right? If you have another antenna that you want to grab more data, you're not going to change Mother Nature, right? You're just going to collect it. So think of a code being like a experiment. If I build this experiment, it's like, I'm going to collect things. And then I want the ability that I can just peek in, subscribe. Maybe some of that goes to a file system. Maybe some goes to visualization. So just think that if everything's publishing, but it all goes dev null, then nothing. But if someone's all of a sudden launches something and now they want to see some variables, they can. That's the principle of ADIOS. I hope that makes sense. Norbert, did you want to say something?
No.
Oh, okay. You agree, right? Good.
So, no. I'm starting with Andrea, so I don't know what you.
So what I'm trying to say is that, so we've worked with lots of different applications. And I guess one of the advantages I've had being a physicist is it's easier to go in a room and other physicists will actually like talk to me. Whereas like a lot of computer scientists, they don't talk to all the time. So generally, like, you know, the physicists are the easy ones for me to work with. And it's trying to understand what is the science they're really trying to do and can we help? And we can't help with everything. But generally for a lot of these IO, other issues, we can help a lot with. I don't want to get, you know, I didn't get into everything. The other thing, again, is this whole concept of staging and all staging. So where it started was a very simple thing. You know, that horrible variability. Well, what if you have this large supercomputer and generally most people won't use every node? What if you have a few extra nodes? And what if you actually just had the data, move that in the network to these other nodes, and now continue your computation and let them write? So staging was originally thought of as, could we just have this asynchronous way to write by just using these other nodes? The community really bought in, and they said, well, instead of these separate nodes, let's put in this concept of a burst buffer. So we just put NVMe on each node, and then we do it. But the problem is that you're sharing the network if it's on the same NVMe, but you have more concurrency because you have more nodes. So then there's all this stuff. But this is how staging started. This didn't work well. Mainly it didn't work well because generally we put it to separate nodes. And now we have to drain from that node, but it's only a few nodes, which means we only have a certain amount of concurrency. And that never could actually keep up with the speed of these large scale apps. So what we found was, you know, when you tune the IO really well, it's really hard to make staging if you're just writing work better. In some cases it does, and we had that. And one of the ones was with the pick on GPU guys, and they did do that. But again, it's like special cases. So the other thing is like in staging, there's all these options about transfer mechanisms, placement options, scheduling options, what we'll call refactoring, which I talked the other day, I won't talk too much, and about storage options. Just have ways so that you can use ADIOS, and then you can stage your data somewhere, do a bunch of analytics. That could be on the same node, you know, with different cores. It could be all over the place. So let me again speed this up a little. And one of the things that we found out, and this is again dating me back 2010, but this was, we had all these particles. We really wanted the particles sorted, but it's really expensive to do a parallel sort. In this case, we had 1 trillion particles, and we were doing that at scale. So this was can we do part of a sort? So think of like a map reduce, because this was looking at map reduce like algorithms. And then using ADIOS to stage the data, do these extra operations along the way, index it, blah, 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 and then write it. And this worked really well, which was then going for a philosophy for doing more of this. Staging techniques work well for AI applications. For a lot of data that's like temporary transit data, we can stage it. This way we can actually have things iterate and convert much faster. One of the things we find out is that there's a lot of variability when you're running all these separate ensembles from AI. So you can actually mitigate a lot of the variability. And that's what the graphs are showing. And I'll skip that. I'll skip this. And I'll say, again, this is working with Korea with their large fusion reactor. And what we've shown was that if they can actually move the data, stream the data, we were able to have their processing go from 12 hours to 10 minutes. This was like a fusion highlight. And a lot of it really about saying something very simple that don't wait to the end of the day or the end of the experiment. Scale up your analytics as well. So there are a lot of enhancements here. And it was nice. We used the same parts that were developed for SKA as for this. So this was Jason Wong who helped with this as well, be able to help automate this pipeline for processing data. And we're excited about it because ITER is being developed. Eventually, that's the main fusion reactor that will be used in the US. We'll have essentially no large reactor. We have no large reactor now, which means all the data is remote. So how can we actually start processing and understanding things for these long-running experiments? This is what we're doing in our fusion code for ECP. So one of the things is, once you have this concept of pub sub, once you have the concept of fast IO, then if you're doing a mathematical strong coupling, rather than putting everything in the same application, and in this case, it was different groups developing, well, one was a core code, the core part in a fusion reactor, the other was in the edge part of the fusion reactor, and it's saying, hey, we can just do staging, each separate application. We do communication between them. In this case, the underlying technology could be things like TCP, it could be UDP, it can be things like MPI, or it can be RDMA, or it can be files. And when you're developing and trying to get the strong mathematical coupling right, you want files to start with, because persistence, because it's complicated in numerics, and then all of a sudden you want to turn on the staging without changing your code, which is again the advantage. Write your code the one way, don't change it, and then make it work. This was highlighted in ECP, and again with the coupling, I think that was important for us. Let me just go on a little bit. I don't want to talk reduction today, but besides the fact that reduction to me plays a powerful role in IO. And when you can actually write data really fast and reduce things for what scientists, and this is coming from the climate E3SM code, all of a sudden they can write out with much higher temporal fidelity and spatial fidelity instead of all the statistical averaging and things that they thought they were limited by IO. And all of a sudden you allow them to get more accurate cyclone prediction in the simple cases because we have more time steps. And now you're not like, gee, you know, did some cyclone happen, but it was a short cyclone and the one case doesn't get it. So, you know, now you can get more accuracy in your calculations or in your deep analytics. Okay, this is just showing a video. Remember, you're going to have to hit if you can. It's not playing automatically. So one of the things with ADIOS, this is just things that you'll do today. When you run an application, you can just run other applications. And there's ways that all of a sudden, the application has no idea these other applications are running. You're visualizing the data from Python, you're computing a PDF. And what you'll see is the simulation just progresses. it looks slower because this was run on a virtual machine, so it should be. But when they're separate nodes, it's not. But here you're filing, you're just firing up visit. Visit thinks it's reading from a file that just keeps updating. And your app has no idea that this is happening. So your app just runs normal. And then what happens is that you can kill things. And I think that's in a few more seconds in this video. There, we go visit. Okay, and we're killing things, and the application just continues. And again, it's only slowed down because it was run on a VM for this video. But then after you kill it, you can fire them back up. So again, thinking of things that, why should the application care about all this extra processing? It's just programmed one way. So you can just fire things up, kill them, go further and further. So we have a lot of applications. This is a small company working in Fusion out in Irvine, California. They're building an FRC, field reverse configuration reactor. It's kind of linear. It's kind of cool for a fusion reactor. We're funded by Google. Hypersonics, low tomography. This is the pick on GPU where they're looking at cancer and targeting with their accelerators, like tabletop lasers, targeting tumors through these accelerators. This was with a weather code WRF researchers in Tel Aviv. This was the JAXA, so that's in the US we say the NASA equivalent, but in Tokyo, you guys in Perth, Sandia with this is the main guy for lamps. So there's all these different codes that we've worked with and partnered. And it's really exciting for us when you hear about all the physics, all the science that they're doing. And sometimes you get to be on the paper, and that's really exciting for us. And this is just showing again that, as you start putting in a lot of the things that we do, there's a lot of new physics, a lot of new science that can be enabled for the scientists. So it's not just our computer science, not just ADIOS, it's how do we enable the applications? And that's what some of these, this is the global tomography. And if you note this, this was back in 2020, you see 7.5 petabytes of data is produced in a single workflow step, which is quite a bit. So they really had an IO problem. And, in their IO, you can see that at that time, we got down from 94 seconds with IO to 156 seconds. So and where they were before was crashing the machine. So we went from they couldn't run to they could run, and it was a huge performance leap. All right, this is now Norbert. So before we get into now all the concepts, the API, does anyone have any final questions?
What is it run? Just to clarify it in my head, where did ADIOS sit between what was going on in the simulation and what?
Well, we're gonna show you exactly how that happens, but the way it happens is the following. You have an application and an ADIOS. Norbert's going to show you whether you're going to storage or you're going to whatever, you're going to put data. You're going to do puts. That's your application, separate application. If I said in that case, now you have visit. Visit has an ADIOS reader. So now you run visit. On both sides, you say in this case, you're going to use an engine called SST. And now what happens, there's some options. And now, hey, when the one's there, the other sends to it. And that's it. Make sense?
Yeah. That was what I was missing.
But what we're also maybe showing, besides the kit where a person screwed something up, according to Norbert, last night. Yes. Or maybe not. But we were showing ParaView with Catalyst. So the other way you can run ADIOS now is that you can do what we call inline. But now what happens is ADIOS has the put, but now you have another library that's compiled with your app, which has ADIOS and has the gets. And that's just going to use memory referencing And now it's traditional in situ. Which for some people, they think that's better. I would say that most times it's worse. And there's all these papers why it's worse. Because again, the simple fact is all your viz routines, all of them have to scale at the same level of concurrency as your app. And that does not happen. Try streamlined at scale, just and see what I mean. If you have a domain composition. So what I'm saying is it really does depend, but ADIOS has all these options, but you don't change. That's the beauty of it. Okay, Norbert, it's all you. I might get to relax. Right. That's
I think hi, this is Martin here. Just wanted to say that if there is any more questions from the virtual audience, please feel free to unmute yourself and ask them now. I know that Norbert was answering some of the questions in the chat, but if there are any additional questions, please feel free to ask them now.
I will just talk about the ADIOS concept and the C++ API, and then we will have break, and then we will come back and we will start modifying the code, then writing out data. The Scott run the simulation part of that we are. So just some links in the PDF. So we are using the latest release, the 2.8.3. In the we are using a repository from my account specifically for this tutorial. Usually we do more like a demo type. This one specifically is for spending a lot of time and you are not just entertained, you are going to learn ADIOS by typing in GI. So it's the best way of learning ADIOS, I guess. Some other links for where the documentation is, where examples are, where the source code is, and if you use ADIOS, please put your tickets in the GitHub repository. That's the best way of doing it. So that you can hope that one of the enthusiasts who we are will respond to it. So it hasn't happened that if you have an interesting problem, you will just not address. Okay. The movie that Scott shows is here are the links in the PDF too. So you can see two of them. The second one, the first one is doing it through files. The second one is doing it situ. And the point is, it's the same codes. It's just the runtime parameters saying now we go in situ. And that's what we are going to do by tomorrow. If you change your code, we write 4 files, we play with files, and then we go in situ tomorrow without writing a single line.
But so I apologize. The one thing I forgot to do was to really ask everyone what they would like from this, from this tutorial. What is it like you would like to get out of this? I mean, because if it's all random, of course, we'll do everything that we're going to do. But if we found there were certain things you guys wanted to know more than others, we can spend a little time to concentrate on that. I know Norbert doesn't like that.
Oh, there is a targeted question. Who wants Fortran? Who needs the Fortran?
But who wants it?
No, sorry. The tutorial will focus in C++ and Python. But I can show you Fortran code as well. The question, how much do you care about Fortran?
Yeah, it could be in the chat as well. We could do a doodle thing.
Yeah, so the hands-on will be C++ and hands-on. That's what we live with. There is another example that Fortran code and this goes through that and this. Or I can just see, you will get the audience we have. This one, the tutorial, there is a heat transfer which has both and Fortran. That's what I would show, but if you are alone, okay, you have another working example as a Fortran application. The simulation parts, Fortran, and then you can use the analysis in the C++ code and then the visualization in Python. So you can have this mixed language.
Yeah, it's fine. I was just, well, we have Fortran.
Mhm.
If there are any things to know, well, Fortran specifics is good. Know them, but for the training, right?
Right, okay. It's a Fortran 98, right?
Yeah.
Okay, so let's then talk about ADIOS. The concepts and the API. So I don't remember if Scott started showing the ADIOS of the core and it has engines around it. And the first thing of ADIOS is the main goal was designing a unified framework for both file-based permanent storage I/O and in situ storage and in situ processing. So so that is driving philosophy of how we design ADIOS. And the other one is it's not don't want to burden the user with details that they don't know. And so rather giving an assembly language level of everything is possible, rather it's make it easier and have the other ways to like tune for best performance. So the I/O is declarative. Declarative means that in the source code, when you write an application, what you describe is the data that you have in memory and how you want to be that represented as you publish it for consumption. Or if you have a code that reads in data, it's a consumer, then you declare what you want to get. Every process in a product application says what I have or what I need. And there are no calls to say, I want to reorganize all this data on the fly from my 100,000 cores into 1,000 blocks through 10 files on the things, because that's not the concern of a user. That's not the concern of an application, because the application next day will run on a different number of cores on a different machine, or the machine was updated, or you go from GPFS to cluster. So it's crazy to expect from a user to change the source code to optimize it every time when they move to a different machine, right? So from moving from Magnus to Cetonix, if you have to rewrite your I/O code in the source code, that's old school, would say. Yeah, it's not a good approach. So everything that you write is just declarative. Every single process in a product application says what I have, what I want to do, and what I want to read in. And then it's ADIOS' job to provide solutions for specific environments that works well. And that's what the I/O strategy. How do we move data? When do we move data? When does it go to the storage, or when it goes through the network? When is it consumed? How processes communicate during the I/O phase? That's something that's hidden from the user code. It's made these decisions made by the implementation of the specific engines, and hope that this works out. And then this is good for users because they don't need to worry when you trust that ADIOS will give you a good solution. If it doesn't, then you have the issues to complain. And it's good for developers because now we have a framework and there is a new fancy things coming in, like what we started talking here is that a Ceph specific engine to optimize reading back from Ceph, which has a very tight link to the machine. So it's not for performance, but for function. Right? So we could develop a very specific solution for that. And you don't need to change your code at all to use that. You can write to Lustre or you can write to Ceph and you get the good. So that would be the future, like the caveats.
So
Just to work this way.
yeah, just as the caveat, like right now we're doing specific things for ADIOS, if you know what ADIOS is. So it's an object store. We have to do it because of Argonne, and it may or may not exist. Thing is, like, it's similar to Ceph in some parts. So it's like, we've created a separate engine, and then there's different ways to talk to it. We wish it worked the way it was supposed to work all the time, but it doesn't. That's what I mean by ADIOS. But it's the same thing, so for us, it's interesting because do you need to change things, at different levels to be efficient. So that's what we're interested with, with stuff. Sorry, Norbert, go ahead.
Okay, so the basic concept. Self-describing scientific data. What does that mean? It's basically the idea is if you produce an output data set which is on storage, it don't require you to have your notebook somewhere writing down something inherent knowledge how to read that, what's in there, how to process. Self-describing is aiming for saying you have a data set, you have the tools to look at the content and have the ways of reading properly what you want. So it's not invented by ADIOS. NetCDF and HDF5 are good examples for self-describing data, right? You don't need, but an MKIO or a POSIX binary file that you wrote, you have to have somewhere written down, okay, by 0, by 10, by 100 bits, this thing, you get that, right? So that's opposite of self-describing. And it basically has variables and attributes. What we store the data in multidimensional type distributed arrays. So assuming a distributed application, a parallel application has data in separate pieces of memory and represented as a multidimensional array. And it has a basic type of a double array, a complex array, a byte array, whatever. And so want to produce a nice cube, let's three-dimensional, so a multidimensional array on storage that has a single type, and then you can write into this big array from different processes in the parallel application, and a different parallel application can read arbitrary pieces of this. That's all, multidimensional type distributed array. That's what it means. Plus, we have single values. That is a single value across the application or a single value per process. So MPI size is one value, global value, MPI rank is a local value. Everyone has a value that you want out, and then when you want to get information, you have a set basically one array of values from every producer process. Right? Yeah.
So just to clarify, does this allow for concurrent read and concurrent write?
Absolutely, yes, and absolutely no. So depends on your no, it doesn't. Let's clarify your question. It's not, ADIOS doesn't have anything that there is there are producers and consumers, and there is somewhere a 3D cube where you write pieces into it while others are reading it. It's just there is no such concept in ADIOS at all. What is it? There are the producers, a big application can produce a 3D, nice 3D cube of data. And as it progresses, creates new ones, like the steps. Right? So what you already produced is immutable, and then a consumer can read it and can read that. And then the producers can doesn't care about what the consumers do. They just produces new versions of that. Sorry. Okay, so Scott has a different opinion, so I'm wondering what
I don't, just data spaces has always been linked, and data spaces has some of this concepts, which is like, you create a shared space abstraction, you put data in, so you can think about putting in a large image, but as what Norbert's saying, it's kind of like you may want to call it a chunk or what we call a step. You put this portion of data in, and once that's there and you close that step, essentially, I don't want to bastardize this, Norbert, but essentially, once that's there, then someone else can pull that out.
So it depends on his question.
So,
Right, I know, and that's
so while someone else is pulling it out, if the process is updating stuff and it tries to update that chunk,
Yes, so the answer is no, there is no chunks here.
It's, yeah, it's,
This array is produced at one. Doesn't matter, one process or 10,000 processes. This is this. It's being produced, and when it's properly produced, it's end step. It's done. Then it's immutable. There is no updates coming in. You cannot update chunks in an existing state.
so generally when someone said, well, going to like anyone in astrophysics or relativity, like we think of space-time. So time is just another dimension. So what I'm saying is like, if you think of putting things at that time, and now that's done, and now you're putting the next time, because now you're adding to the dimensionality of time, that will work. But if you're saying spatially, now that will not work because, you know, it's different.
But you could structure your steps, right? So that there is normally, if you wanted to, right now, write all the X first in a step, end the step and go, that's now complete, and that can be consumed by a consumer. Because X, you've just enclosed one
Yeah,
bit.
let's continue on that.
Yeah,
one.
yeah.
Okay. So unfortunately, we call it step.
Yeah,
It's misleading. It's blur.
yeah.
The name of the concept is blur. Okay, it's not step. And while I'm standing here, please don't say time. It's fixed now. Okay. Anyway, so that's it. That's what the data is, multidimensional arrays. Okay, so and then attributes are static information like labels assigned to specific arrays or the whole data set, like the application name, the date, the machine, architecture, the user who wrote the code, the setup, whatever is it's just a generic label. And then for every array, you could say, okay, my unit was Celsius. That's usually useful for the temperature variable, say, recorded in the self-exciting data that is for Celsius and not. Usually that makes the difference. Yeah, that's all. And so this is a very old code from ADIOS 1.2 or something. This is how it would look like. That when you list the content of the directory, what's in this data set that was produced, you would see, okay, we have these single values as zero value, it's a real, so it was the float, and the string scalar, which is a string that they recorded as a variable. This is a variable as a single scale, single value variable. This should be an attribute assigned to an array, but that doesn't matter both ways. And so, for example, we have a very simple one-dimensional array of 6 elements, which is integer, and it's just called like hierarchical array. So naturally, you are human, you see this as hierarchy, right? But ADIOS doesn't have that. This is just a string, it's a name. And you are allowed to use separators to represent your data for humans as a hierarchical data set. To organize your pieces of data, they had 130,000 variables in this file because they had lots of this chop up the space. In mechanical engineering is chop up the space to different parts, each described with a separate mention. So you have these lots of domains, and you separate the variables on different parts of the space. And then you have 3D array 8 by 22 by 52. This is a floating point value. It's on domain 14, and they call it that. And then there will be density on a different domain. So they know that that's all right. And but you also have this min max. This is a global min max for this entire array. So in the listing of content, this is a feature of ADIOS that you can see the min max. There was some cost with that associated when the data was produced. Going into the system, but it's pretty useful if you have not a number or inf or a crazy something, immediately know that your data set has some problem. Right? In the simulation, first thing you blame ADIOS, must be ADIOS problem. But if you pass over that, then it means, okay, where did my calculation go wrong, or what happened to this? And then there are even you can get min max for per process, per over the runtime saying what was the min-max of that process, so you can come down. There is any problem. Okay, that's it. That's how it looks like. And so let's talk about this.
So just Norbert, I'm not trying to,
You are trying to.
but if you go back on the slide, just the thing to point out. You know, because there was already questions the other day, like as he's putting them in a max. There are, you know, we had the concept of characteristics or the statistics. We kept min max. At one point, we had things like, you know, mean, we've had other types that can be there. The reason why we didn't include them is in cost. But now what you're seeing with GPUs, a lot of these things are becoming much easier again to calculate. So we do have the concept of extending, you know, putting like variable, you know, variance, other things. If it's useful, those are things which can be done. Is that right, Norbert?
Whatever Scott says is related that you are opening a ticket on GitHub to tell us that you want this. Okay, you got it? What I'm saying is what Scott is saying. Yeah, but if you think you need this, don't just be turned off instead of saying, I want this.
Well,
right?
But that's the important thing I'm
It's
trying
important to
to tell you, because we're driven by our customers. These things are, we've had them before, they can come back. There's reasons why we had to drop it, but they can come back. So if there's things that you would like, just tell us. Sorry. Go ahead.
So min-max is on default. By default, is turned on. You don't need to be concerned about this until you go to when you have blocks of data on a single process writing a gigabyte. Then calculating min-max has a time. And so it has that cost can concern you at very large scale with huge amount of data. And maybe you say, but I don't care about it, so I don't want it, then you can turn it off. But usually it's a useful feature and it doesn't work that.
So I've got one question. Is it possible for us to modify that data structure
To provide a different value for it?
for different purpose? Not specific like for density or velocity, but for other things.
Oh, I'm sorry, I don't. You want to modify what part?
The data structure.
No, this is one application's out.
One thing.
They define, I have a space and I chop it up into different domains, and each domain is a triangle or cubic, whatever.
Yep.
And I say, I want density because my simulation has density. And this is just, for you, this is just a string. You place whatever is the string.
Right, okay.
The types are as a set of what you will have in C++ or in Fortran. And the dimensions is you specify it. So
Okay,
nothing concerns for you here. Is just, this is how it looks like for one person.
okay.
Okay, I thought that you want to modify this.
No, just, yeah.
Yeah, okay. So what I meant by distributed array. So this is, let's say we want to produce a 2D array. It's just a simple 2D array, but we have multiple processes producing that data and they have a layout in memory. So this is a 2D decomposition of a 2D array, right? So everyone has a piece of data. So how do they describe to ADIOS what the output should be? So there is the fact, how is the data laid out? The other is what I want to be in the output represented, right? So in the output, you don't care about, you have to tell the consumer that this was produced on 10,000. You don't care, right? You have a 2D space or a 3D space. You want to say these size. So this is what you tell others. Hey, create a double array which has these global dimension and that's the shape of the array. But then every process has to say, okay, my place in that array is at a given offset, right? So you say my place starts at start, and then you give the position in offsets, and then also my part is this size, and then you just place it. So do you have any questions about this? This is very simple, right? If you ever use any service guidance. Okay, so
Norbert,
yeah.
I imagine if there is any
endianness is managed internally by normalizing to a given endianness or both. You still have different endianness somewhere? I'm basically yes. Problem is, for the last 5 years, we had no access to different endianness. So it's at this point, I would say untested. We always had it. No problem. You produce a data set on a big endian, you move it to somewhere, you have it in there. The tricky part, if you would be able to connect two machines and do in situ, which they could see them
on the WLAN use case that you showed.
Yeah.
Then it could be a problem like.
Well, that's what but TCP based, I will solve this by doing the network file format, which is not big endian, not big endian, and it's always on. So the networking libraries already take care of this. So it's a convenience, but this is you do it twice and convert on both. But if you have a data set produced on big endian machine, you copy it to another machine, and now you read with a little endian code that the data is big endian on the disk. So then ADIOS will flip the bytes every single time. So the conversion is on the reader side. I would just say it's untested at this point because codes are always modified. We have this in the code, but it's basically untested on GitHub. We have lots of virtual machines to test different architectures. None of them is big. So,
Do you guys have machines though that are?
no.
Yeah, I mean, that's,
We might have one here, but I don't know.
right, but that's the problem. If you don't test software, how do you know?
So, but it might be that's the problem of the past, and maybe, but you don't know if it comes back. But officially, we still support it. Oh no. Okay, so anyway, so it's clear to me. But so now let's take off the implicit assumption from here that you don't need to limit yourself thinking, okay, every process produces a nice contiguous piece in a 2D space, right? So these are all valid definitions. You can create them, every process can have 0, 1, or many blocks of data that they contribute into this big space. So you don't think that you have only allowed one to one. So you can define these multiple times and put multiple blocks. It's not required to saying that everything is neatly overlapped. This is the normal use case because this is what majority of users expect to use, right? And this is what makes sense. But nothing prevents from you, because it's a declarative thing. You can intentionally create blocks on every single process randomly, different offsets, different sizes, and just fill out your space. So you have lots of overlaps. This is totally fine. ADIOS is going to write this for you. And when you read it, you see it to a nice 2D space. This is what you see when you list the content. And when you say, I want to read a portion from here, ADIOS is going to deliver it. Which value from this block, this block and this block are overlapping. So you have two copies of this data somewhere. Which one you get is none of your concern. I mean, if you're a consumer, right? You get one of them and you should be happy with any of them because the producer declared that this is a nice 2D space and just contributed two values somehow from two different processes in the same space. But the presentation to a consumer is you have this 2D global space and be happy with it, right? So, but it does work, no issues with that. The other one, no, I didn't say you have to fill out the whole space. And this is an important distinction from other libraries. So ADIOS doesn't allocate, when you say this global space, ADIOS doesn't allocate that space in the output storage. Say, so if you create a million by million by million cube, you don't just fill out the space, the disk immediately. There is nothing happening there. And then you just write sparsely blocks into this space. Then that's what is going to consume this space on the disk, or that's what will go through the network or in situ. These are really empty space. It's not going to happen be written, nothing to be encrypted. But the whole space is represented to the consumer. And if you specify a region where you want to read in, you have to provide a memory for it, and ADIOS will you allocate the space. And ADIOS will bring in the data that adds data and does not touch your allocation for where there is no data. So,
To be clear, the idea would be that whatever you initialize that memory space as, you just leave it completely unchanged for like the ability.
exactly. So, the program, that hey, NetCDF has these undervalued. That you say wherever I don't have data, put this undervalued. But what NetCDF actually does, it will allocate on this and will fill out with this code with undervalued. So when you read in, you move a lot of data of undervalues. But the nice thing is you define what under is. 0, -1, minus infinite. Right? And here in ADIOS is basically, if you do a malloc, you have random data. If you do a calloc, you have a zero. Or you create a vector and you initialize your undervalue. Then ADIOS is not going to touch it. And you get the data pieces, but you don't get anything, data movement. So it's pretty fast. And because we talked about, well, we talked about the bingo stuff, that we assume that there will be a lot of empty spaces. So that this would be useful.
Right. If at the beginning of your computation you don't know the full extent of your vector, of your array, is it a valid strategy to declare it's pretty huge and then just fill kind of the portion of the array that you know that you accumulate data over and then kind of close it to that?
That's an excellent question, and let you say that's a valid. I mean, yeah, but so the only problem is that this global space definition is going to be represented to consumers down the line, and if that consumer is someone else, you may mislead them whatever you have there, right? But it will work. I mean, you can create a 64-bit packs as a dimension, and it's fine. It just ADIOS doesn't do anything specifically with that, but it assumes that you are going to provide pointers that allocate enough space to it. So no way that you could read the whole array.
What type of code does that?
Vortex or Scott. Vortex.
Okay.
Vortex is doing it. But we need to talk about this thing. So the thing is, naturally, you would assume I know everything in the beginning of my code. You specify the shape, every person specifies what they do, and that's it. First step is atom simulations, particle simulations, those things move around. So the offsets and count, like if you would have a table, one atom per table with the columns or positions, energy, whatever, then the number of atoms on every process is different every output time as the time progresses. So they have to change this every single time. The number of atoms doesn't change usually. So you have a table of n atoms, but the contributions change. In particles, they collide, they go out of the system, new ones are injected. So the total of n is changing every single step, and the decomposition changes every single step. So definitely you can change this every step. Every block, you can change this saying, okay, my array size changed. This n is changing. You are allowed to do that. And the last point to specify a shape for a given step is just before calling n step. So you can define whatever you wanted, arbitrary shape. You start your calculation and you produce this data you put in. And at the end, before you say, I'm done with this constructing this step, you could say, my shape is n. This is what Vortex is doing at very largely. So yeah, it does work. We have to put in these fixings for they allow to postpone this information to the very end. Right?
Right. Yeah, because we can use the ADIOS information for Kasa or the radio library for writing data. And we did this kind of infinite extents for the because we don't know in advance at that level in the software stack how much data is coming in. Like we see really at a very low level compared to the end application. So we don't know the information yet. So we just declare the variables like input size, about 64-bit size, and they were right, and then we end the step. So far has worked, but we didn't know what were the consequences.
Yeah. So it does work, and so I see that good. So your step is so big that you want to construct it over time because you don't have enough memory to deal with all the data that you want to actually produce. But synchronized step, so right. So and that's what frequently if you're not Vortex X wants to do the same thing is to construct over time because there's so much variables and so much particles that they just want to do this flush data, do this during constructing a single step which is bigger than the memory of the product application and produce that and then come up to this shape size at the very end. So it should work with BP5. So that's the things that at one point BP4 is the default file format and probably work, but something is going to break and then that's time to say, okay, what is the difference with the new version is 5 and if it doesn't, if they are. So the nice thing is with this approach, you specify the shape in the beginning, when you list it, and then you produce 1,000 steps, then the consumer has an easy time to read that because you have a time as an extra dimension, you have a 3D array here with 1,000 times the XY, and then you can read even across time. You have a 3D to read. But if you change the shape every single step, obviously it just tells you there is no global shape. These dimension will be underscore telling you that this is changing over steps. So if you see underscores here, that's not an error. That means it's changing over steps. Okay.
So here, the step actually means an instance of your simulation.
That sounded like to me like time step. So no. This is the most important slides. Happen to be the most important slides of the whole ADIOS tutorial because I start to realize that the step concept in ADIOS is what really distinguishes from any other I/O libraries, and this is the core concept that allowed us to do the cool stuff. We call it step. I managed to take out time from this word. It's a ordinary time step, but it's not time step. And it's step only in the concept of saying that trying to define the producer outputs a set of variables and attributes as a step. But that doesn't tell you anything. Okay, there's a constant over time or there's a single point in the calculation when you say, okay, now I get rid of every data. A step more like say a step for you, think about it, your consumers. And basically you write your applications with the goal of writing papers or discovering something, and you have consumers, analysis and visualization and whatnot. And there, what is it for a consumer to see all the data that consistent in some sense, usually, if you have a simulation that simulates in space and time, progresses, then you have instances in time that you want to say, okay, all my variables, pressure, density, temperature, whatever, you want a consistent view of it, and that goes out into the step.
Can I try if I understood it correctly? A physicist might find it easier if you say that this is a point in the phase space. Your state would be equivalent of a point in the entire phase space that you were trying to.
Probably, I don't understand, but probably, yeah. So like
it's like
the quantum codes don't really have the QMC packets, for example, doesn't have concept of time. They just optimization or quantum walks. It's just they just output phases in the simulation, saying this is my current state in simulation, progressing towards a final state, which is the optimum or minimum or whatever, right? So there is no time to relate
Sure.
to.
So state would be the right word, I think. And state also creates this inherent confusion that it is somehow.
That's one I agree. So step is totally confusing.
But I think it is a state of your,
Should I modify the slide now?
What? Sorry.
We can modify the slide and
And then
tonight you can work and get that
Yeah,
out.
but Yes, it's not a physical. And just because we make physics at the end, it will compute others. The best way of saying it, wow. Everyone's perspective is something else. From an age of.
And is it something becoming beautiful? That's the way I always understood steps, is that you start something, put in what you'd like a consumer to constantly view, and ends up being beautiful.
Yes, exactly. So basically, it takes goes around one big problem in IO. Be that in NPI communicates. You have a bunch of different pieces of data that you have to send over from A to B. B is the consumer. Even in NPI, you say if it does, it's not a single double array, multiple of them, either you create NPI data type, they elaborate it, or you just do multiple NPI or gather or whatever, send or send whatever from one to the other to exchange data. And you don't use the fact that while you send over U and or P, and before you send P, the consumer could do whatever with the T and mess up itself, right? You don't do that because you write the consumer code and you know that you want to have T and P variables over there to have a consistent state of your computation. So there is a bunch of different data sets that you want to share with the consumer. And if you start writing data in a discrete NPIO or with HDF5, you would be able to look at the content is changing all the time. You get updates into your data set. Oh, I have T, let's read it. But yeah, you don't know when it's fully produced, and then also P. When is the P coming, not, or so there is no higher concept of as a set of saying, here is the consistent view of all the data that the producer at some point gives us, the consumer. And once you get access to that step, you have access to everything, and you don't need to worry about any changes because it's immutable. And you have, even in staging, even if the data is stored on the producer's memory, the step, once you get access to it, you have the luxury of reading without concern of, oh, is this going to disappear under from me halfway? Is the data going to be consistent? It is. So you can, that's what ADIOS delivers. The step is something that bunch of data together produced at some point, and then the consumer can safely read the content of it. And basically that's what it tries to do. But as a consequence, the IO becomes declarative on the consumer side because we can tell ADIOS, I have all these variables, all this, and every process, and then say, produce this step for me. ADIOS has a lot of information, your pointers, data pointers, where the data are, and it can optimize data for the entire data set instead of, if you write P, ADIOS can only take care of P. And then you write P, ADIOS can only take care of P or whatever IO library, right? But ADIOS has the luxury of taking care of your entire step and move. And the consumer has the luxury of, I just want this, I want this, and it will get it, right? No concern of when you should get that so that you are constant. So that's all the ADIOS step is really. It's very simple. It should be always bogged down on what the name should be. Right, so that's what leads to that ADIOS has a unified API for in situ and file-based because it's all step-based. And these are nice pieces of chunk of data that goes being constructed, being produced, and the consumers can get it. This is the what is ADIOS to be declarative, so that you just say what you have in every single process. This is what I have, please take care of it. Consumer says, this is what I want, please take care of it. And then can be optimized implementation for whatever media to deliver the data to the consumer. Okay. So, only one example, but why would you choose ADIOS if you say, like, what does it take to implement an asynchronous I/O implementation that can work in the background while your computation moves forward? Any other I/O library that attends to that, what they will end up is to provide you a new set of API functions tuned for old school, like multi-threaded asynchronous programming. So it gives you, okay, now you have the ability to control when data goes to disk, or variable, or, and then you have to do the synchronizations for yourself. You have to check for the status of this. So it gives you an entirely separate set of operations. You have to code in your code. If it doesn't work, sorry, you can debug it. Once you get it working, it works for you, but it's not so great. You want to go back to the simple one. Okay, now you have to modify your code again. So it is neat because you have full control. The problem is you have full control. In ADIOS, with the step concept, we can just create an engine specifically tuned for asynchronous operations, and you just turn on. Oh, I don't like it. Turn off. No changes to your code at all. So that, I think this is a big advantage. Not everyone would agree to that before they can say, I want full control. Okay. Yeah, so that step is not related to that time step, but usually applications that progress in time and produce a given time step, they say, okay, I want the checkpoint. I want to write out all my diagnostics now. So that's the way you write out the puzzle. So the concept with the step thing is, so step can be big, and in the ADIOS 2.8 with the BP5 format, even with BP4, now the step data could be bigger, much bigger than the entire memory the application has. So the step can be constructed over computation time. So I start at step, it's big, I will fill up the data and then we say it's done. And there might be a lot of I/O involved in that through the disk. So there is data lying around, half-baked data lying around, but it is inaccessible to anyone. And if the application doesn't reach end step properly, that data will be inaccessible. So if you produce 100 steps and then constructing the 101, something goes wrong halfway, that one step 101 is not going to be visible, and the step 1 to 100 will be intact. So this is an important piece here, that you don't end up with a half-baked state in your data set. You either, with like a transaction, you either succeeded or, even though if you get garbage on the disk, you wrote 0.5 terabyte already, but it lingered there, but it's not accessible and it doesn't affect anything that you wrote before. Yeah. And so basically the step is just the bunch of things that I'm writing into this output set. It doesn't need to be the same temperature, density, whatever. It can be a totally different set of variables. So it's up to you how you want to mess with this, whatever you have. You can put a different, it's really the step is just constructing what my consumers need to be as consistent pieces of data that they can progress. Right? How would you process your data? And that's all. Okay, so that the consumer is guaranteed to have access even in any staging engine. This is guaranteed. So the producer, if it calls the memory for this, and the consumer is processing this data, the producer is not allowed to throw away that data. It might to come to that point where it's blocking because the consumer is too slow and it cannot process because there is not enough memory to start new steps, right? But yeah. So we'll see that examples tomorrow. With our example, we will play with them. And that's it. Enter a content of step must fit into the previous memory as a copy. Was true for 2.7. It's not true anymore because some applications really push hard to get that limit. So that line is static. That's not true.
Is there a limitation in any way?
Well, so you will going to pay some cost. So yeah, the Scott showed, oh, this application does 2 terabytes a second output, and basically running on almost the 3/4 of Summit, and it's really using all the GPUs and all the memory and dumping insane amount of data. It produces 7 petabytes in 15 minutes. And so, but it runs longer because we can't save that much. If 2 terabytes a second, it still takes a quite time to write 7 petabytes to the disk. But if that data, well, so those many steps, so that's not entire 7 petabytes at once. It's 250 terabytes at once. But that's actually not, that's 250 terabytes in 130 steps of data crunching. And then it's different sets of data. It's a big ensemble. And so it's lots of data produced all together, 7 petabytes. But if we would change the code saying, oh, I'm producing so much in one step that I have to save data in the middle and then continue and save more. Yeah. I don't think it will get 2 terabytes a second.
Right, okay.
Somewhere you will pay a price.
Yeah.
Okay, no limitations in the coding, but the functionality, but somewhere not every possible code can reach the bandwidth of the file system or something. But I don't really have experience, so I don't know exactly. Okay, so okay, let's progress because then we need to start coding, right? Okay, so C++, ADIOS written implemented in C++, so it's basic. Has objects. In the C API, it doesn't, but in the Fortran API, then it has again the objects. So we use the 49 types to have an ADIOS object. The ADIOS object is basically the NPI unit piece. This holds everything else. So you need to initialize these, and then everything is created from the ADIOS object. We have a variable object for every single data variable, the n-dimensional array or the single value. We create a variable as an out. So your pressure, temperature, density for is each a variable. Of course, we have attributes. IO is the blah or the step. So IO is the object that holds all the variable definitions and the attribute definitions in a given time that goes into an output, or that comes in as an input. So IO is strongly related to the step. This is the object that we have to ADIOS object to create an IO object for checkpoint, to create one for diagnostics, to create one for analytics, so whatever have you, right? So you create just a bunch of IO groups which would be related to a few files on your system that you write checkpoint and frequency, then you write the files. And then you please hold it, and then you define variable. IO has the function to define variables and attributes. And then engine is the object that is created at open. So when you say open, that the IO has an open, this is the one, okay, now I'm going to start an output stream or starting an input stream. Engine is the object that was chosen at runtime for the media that you want to use. And so that's the BP4 file engine going to write a BP4 file or read from a BP4 file. And SSD is going to make connections to consumers and producers and establish a over network stream. And operator is a class to hold functions that operate on the data while they transit. So the compression is an operator. Each compression library is provided as an operator that you assign that I want to compress my pressure variable with the DC2 compressor because it fits my application. And so then that's going to work on the data when it goes in and go and decompress when it goes back to the consumer's memory. And then it's transparent. So that's the point of the producer consumer doesn't have code to do pressure, and they just want us for the service of the data. Okay, that's all. So the API looks like you include the ADIOS header, and then you create an ADIOS object. So yeah, the pointer is not going to work. So anyway, so you create an ADIOS object, and it has actually it's really, well, anyway, it has two optional arguments. One is a config file. The config file is well, actually that's an XML formatted text file where you can have runtime options for running the applications now. Not required, not even suggested to use it. This is the shorthand to have something for users, but if you applications frameworks usually want to control the runtime parameters themselves, and they introduce options, how you start up your application, how you describe options, and then you want to control it. So that's the proper, they do it in C++, but this is the quick and dirty access to, okay, here's an ADIOS application, here's the config file, you just, here are the options in that. And the other one is a communicator. So it's parallel, so you pass a communicator, but it's not required. You can have a serial, just a single process doing I/O. You don't even have a communicator. So the only rule here is that anything that you do under this ADIOS object, every process has to be under this communicator. Not every process of the communicator must do I/O for everything, but so this is a parent communicator for everything. And every process is going to have to be called and they will read the config file, but otherwise then you have more options. But yeah, that's the only rule. And you can have multiple ADIOS objects during the lifetime of your application. It's not required for one, but it's easy. It's nicer if you just have one. Then IO objects, they declare IO, right? So the ADIOS object they declare IO, and you give a name. And this name is only just a string to refer in that config file that you want to provide runtime options. So this is baked into the source code. It cannot be modified by the user, but then the user can refer to this in the option file saying, for the checkpoint restart IO group, I want to use EP4 box. And for other one diagnostics, I just want to do something else. Okay, then for the variables, as you described it, every process who wants participate in creating the variable have to define the variable and use the type. Give a name. This name is just a string. This is what shows up in the output as a status and those big domain and density, whatever. So it's whatever, it's a string. And then you give the shape of the global shape. This has to be same on every process. And then the offsets and the starts and counts on every process is different naturally. So you do this define variable to be able to write. This is the definition, but then later there are functions to change the shape and change the offset count. If you write multiple blocks in a single process, you will have to change this shape to say, now this is the definition and here is the data, and then change the definition and then to describe multiple blocks. You don't need to define the variable twice. You cannot define it twice. You define once and then you change those parameters. And this is how you write checkpoint files. You create an engine by calling open, and you pass a name. This name in a file-based engine is basically the path to the file, while the DP is a directory, so it could be a directory. Otherwise, it's a name that's used by the consumer to find you in a staging environment, so you have to use it the same thing staging engines. And then you have write mode or read mode or append. So you can have an existing file and append. Well, that's a write, read, and append. And then for every variable that you have the pointer, you say, hey, writer, here's the put function for this variable that I just defined. This is the pointer. Whatever in your man, this is the application pointer. So you have a put for every variable that you define. And then you just close the row. That's all you need to do. The details are in the definition, right? Well, yeah, so the only tricky part, which you have to get used to it, After quote, before close, you cannot modify this pointer data. So because what this declaration means is that between these open rows, I have an output phase for writing a checkpoint, and here you assign the variable, the pointers to have all the data through the variable definitions that ADIOS have. So it's okay. You give me this pointer, I'm going to move this to the consumer or the storage at some point. After that, you can change. Okay, how do you read this back? Very similar. You create an IO object. You don't need to use the same name. That's really just for if you use a computer. This is irrelevant for other things. Then you open, and this name refers to the data set. So this has to be the same as the writer does. You do read mode, and then instead of defining variables, you inquire them. So in this code, we know that we look for t, and this was the published name. So we inquire the variable. So here in this example, we know that we are looking for t, and it has a double path. Right? It's true information already, you know, because you are writing your application. If not, you need functions to discover the content. And then you get this weak variable, just like as it was defined by producer side. It has a shape, and you can get it, the global side of shape. You can even get the list of blocks, every process producers, but that's not usually not relevant. You don't need that. You decide what part to read, you allocate memory, and then you say, hey, get me this variable and put the data into this pointer. And so this pointer must be allocated. And then you do close. And the important thing to remember, get doesn't get you anything. So besides step is blah, put and get is X and Y in ADIOS. Any other English name just confuses everyone. Put was associate this pointer of the data with this definition of variable. Get is sometimes please, I allocated memory, please bring the content related to this variable whenever it's convenient for you or yes. So the thing is, after close, T data can be used, but here you can't. This is very important to remember because otherwise, you don't, whatever you have here allocated, the data is not valid. So you don't get the data until something happens. Doesn't say that.
It doesn't mean just talk about steps also rather than just open close.
Well, yeah, so that was just checkpoint.
No, I know, but
the thing is, put and get has a third parameter, which is say sync mode instead of deferred mode. Then it goes into action. You tell ADIOS, I want these now. Input, that means I want to reuse the same pointer for another variable. So if I use my code of producing output variable just for the sake of outputs, this was not computed. So I just allocate one placeholder and then I calculate one diagnostic. Here it is. Calculate another diagnosis in the same memory space. Here it is. It's an ugly thing, but people do that, right? So you can do that with the sync. And the get one, you have to use sync when you want to say, okay, I want to get the global space and that's stored in single values. I want those single values now to make decisions who is what the other values. So you have an option here, sync saying, please do it now. But the default one is just all deferred and has a semantics. So the point I want to make here is that this was checkpoint writing, and this is, well, XGC checkpoint writing is the forefront. So I would like to say this is the code snippet from XGC, but it does the same thing. There is nothing else to do from the coding point of view of saying, I want to write a checkpoint, and then they get a fairly good output performance on submit at large scale out of the box. What if you have NVRAM on every single node, local node, which is distributed, it's not a global file system? What do you need to check? For ADIOS, to write a checkpoint, nothing. you can just, but that's because the BP file format is a directory with subfiles, and every file is only generated on a produced, written by a single process and some node. So it naturally fits a distributed file system, and it can be dumped to separate NVMEs. You can't read the data from other processes, but for writing the data to NVMe, you don't need to do anything, just the same. Okay, let's go back. So what changes for if you want to write data for humans? Because the checkpoint list is really for the same application, so you don't have any freedom, right? Anything that's unimportant. But for if you do and analyze this data, you want to do attributes to describe your stuff, so in case someone else wants to look at it. And you produce this data over time, so you have multiple steps. So the code only changes in the sense that you must change this, just be nicer and call your variables more human friendly, and find attributes saying the temperature variable has a unit and the value is C. This is a string scalar. You could have a value scalar in any type. And then what it shows up in the listing, yeah, temperature has a unit attribute. It's easy to process by humans and code. And if you want to produce the data over time, between the open and close, regularly you do a begin step, end step, and you put all the put calls in between this. So to really separate your IO phase from everything else, you have computations here, whatever you do. And I say, okay, now I have a consistent state. I want to put all my variables. Here begin step, before all the puts, then end step. Now, in your case, you would have, this would be big because then you would have new phase of computation and whatever. So there is another function to call whenever you are done with phases where you say, I need to get rid of data because there is not enough memory to perform data writes. There's a special function called to flush data to this makes more space. And then end step is really at the very end of your loop saying, now I'm really done, now a consumer can get access to it.
Now in not in my case, but in the vanilla ADIOS writing case, T doesn't need to leave until block, right? It needs to leave only still and
Excellent question. I just forgot to say, yeah. So the life that this deferred mode saying, don't change it until end step. And in your case, don't change it until you do the perform data right. So that is whenever you know semantically that the data is going to go out. So you don't know what an ADIOS engine does, asynchronous or synchronous, it's staging, it's buffering, it's whatever. You don't know at when it is going out. Just no way to tell, no way to check. What you know that if you call end step, that's a good barrier for that. If you don't have end step, a close is a good barrier. And if you have perform data right, that's a good barrier. So that's the only guarantees there that you can really.
So the form, the
Perform data right,
yeah. If you view now it's that block. I mean, I guess the main issue the consumer might not know, but the idea is to then sample the data that's put or no. No, right. Okay. Let me make sure.
It's not visible. And is the one that analyzes the step and will make it visible to consumer. The perform data right is just part of constructing this step. And this is really moving out of the ADIOS ecosystem of functions that they are need to describing stuff.
Yeah.
With the 30 users, 30 desires, but I want to manage my memories and I don't have enough. I want to do something else. That always pops up in framework. You have to have that.
I mean, normally you can do that. If you, because I would be thinking, it's fine for me if I'm doing, I'm doing something in step. Do much computation, maybe have a temporary variable doing one very end step, and I don't find that would not be the complete set of data that I want to write anyway. Yeah. Right, so we'll say temperature and a derived product. I don't have enough memory to do the derived product. Free up all the memory in an end step, like do the end step, free memory, then another begin step, do my pressure calculations, do all the derived product, write it all. In the step.
It totally works for the producer. The question is the consumer codes are happy to.
But I mean, if it's on the fly, maybe it's not so bad, but if it's on the fly, okay. The key, probably the actual file is produced. But if it's on the fly, then probably.
Yeah, but so we will need to see the processing the file. There are two ways. One is you see the whole content of the file, all the steps in there at once, or you go through step by step. And going through step by step has the advantage that if you have 100 petabyte data set of 10,000 output steps, it's hard to open and read. I mean, you still can, but it maybe makes sense just to go through step by step in your whatever you want to. If that fits your container pattern, right? If you analyze it with all step based, then. But you are right. If you just want to see everything, the problem is that in that case, the audio step you have the API of addressing steps has no relation to your application's state. So step and state will be totally different things, and you have to manage this somehow. You have to describe it for the consumer to not get confused that step 25 and diagnostics belongs to step 23 and
And so the future request, describe it, I think that's for step.
So we talk a lot about,
Yeah.
like I always say, like, what's a physical time step? Because things can be produced differently, but that's all linked together. So I don't know whatever happened to it.
Basically spend the first half of the day of talking and it's extending ADIOS concept. Whatever happened to it?
It would be good if you put something there.
Yeah.
Because I've been talking about this for 20 years or so.
Good like finishing a tutorial explaining time.
Okay.
That's how they buy it. Yeah. This is just the advertisement side of the things. Okay, so they want from scaling, so it's 50 small amount of data, like MB RAM. But there is, of course, there is some cost to write. 3, 4, 5 seconds to write to the MB RAM. So there is open has some cost, but there is a bottom, but it's pretty fast. You can use these local environments to temporary data maybe, and then you want to read it back later and produce real data for permanent storage and you that somewhere else. So there is nothing tricky about using these. The distributed file system, the constraint is that the consumer on a different node cannot see the data potentially, even if it sees the metadata saying there is this nice 2D array. I want to read this, and then there is no data for it on that local. So that's the only danger there. Okay, so it's time for a break, I guess. Now on, for the rest of the day, we are going to edit source code. Okay, so after you source an environment, you can check if you have ADIOS 2-config as a command in your environment. If that works, then you source properly. And then you need to copy the tutorial to your home. So my software is on Setonix setup, that your project directory where you edit your own software. That's your directory. And then you can either clone from the GitHub or copy from the courses directory to that. So you need your own copy. Yeah.
After the course, do some testing on GitHub Norbert or GitHub ADIOS II repository. Which one?
It doesn't matter. So, well, I don't know. Once you copy it, you will have it on the my software is not Scorsese01, right? It's your account. Whatever you have.
It's the test account is for the course.
You only have a test account.
For this, yes, I have to copy this to my own account.
Yeah,
which is fine.
Yeah, just copy it over. Yeah. Well, that course is 01/ADIOS. Just copy it to your own account, everything there, and then you edit it.
So you copy everything, and then you will have the ADIOS VM tutorial directory. So, right, it's just it is in my home directory is Pawsey 7. And so now I'm in ADIOS VM tutorial / GSMPIIO. So the first example we start with is GSMPIIO. So you have the slides, I can move forward, yeah. So basically, this is a Grayscale code, is a 3D simulation. You can find on Wikipedia about Grayscale diffusion, reaction diffusion system is. It has a 3D space for simulation. And what we are going to do in this tutorial is that we have a simulation. We are this example is using NPIIO to produce a binary file and read, and then we have a Python example to read a 2D slice in the middle and make a matplotlib visualization of the 2D slice. So this example is written for that using NPIIO binary file, and we are going to work on this to make it an ADIOS code. So first we do a C++ writing code, and then we will do Python reading code. That's the plan. Well, in the 1 hour, we are not going to do the Python reading code. We are going to do that tomorrow. Okay, so this is the work plan. And basically what we want, what we will achieve by tomorrow, we can run this pipeline together, the simulation and the Python code in situ through files, and then we can plot the steps while they are being produced. Right? Okay, so the only thing to know about the Grayscale thing is that whatever I said about this 2D decomposition of 2D array, this is a 3D decomposition of a 3D array. But every process has ghost cells around its own allocation. So they exchange data with the neighbors, and then the calculation has, extra cells to do the computation without communicating to the neighbors. And so this makes I/O trickier, because what changes is that the output array that we want to produce is not exactly mapped with the allocated memory pieces what the processes have. Instead, so each process has a bigger allocation in memory, n+2 by n+2 by +2, whatever. And we want to tell ADIOS to move the data +1 in every dimension from +1 and only n by k into this place, right? And so this is also a problem for the NPIIO code. So this NPIIO code is doing the same thing. So this simulation has both cells. And we just have to watch out for that. Instead of the two pieces that we tell usually now, you're saying, my process has a starting offset in space and has a size in space. We have 4 pieces of information. These two, my start in the produced data set and the size that in the output data set, also the size of the memory allocation and my offset in that allocation that contains the actual data for 4 pieces of information. In the source code, we have to identify that and then see the NPIIO and the order. So this is the extra stuff compared to what I was talking about before. There are some slides from the NPIIO course to describe this, how is it done, but let's not spend time on NPIIO here. How do they do it? But it's in the source code. And let's get to know the application. So we are in GSMPIIO. I remove my build, so let's just go step by step. So let's build this application. So I create a build directory, right? And this is a CMake application, but we are not going to spend time on CMake because that would eat also hours to talk about and just configure this CMake. So this will this configure it, and it's already set to use ADIOS because we don't want to spend time on editing the CMake files today. So it will just build the code. We have more code than I'm talking about. The Grayscut main writer, that's the Grayscut simulation code. We have a PDF calc, is a C++ reader which does PDFs on 2D slices. So it produces a lot of PDFs. And then there is a Python script to visualize that. And there is a Python script to visualize the Grayscut example. So there is more to do for your homework. But we are focusing on the Grayscut simulation and then the Python code to read it and plot the GS plot. But so now we have the code. We go up, and what we run is, well, how do we run this? No, sorry, actually, so we are on a supercomputer. So we build in our project space, and now we have to install it. Okay, so actually I messed it up. So the CMake, we have to tell where to install it, right? Install prefix equals my scratch slash gsmpio dot. Right, so following, so we have to tell CMake where to install it. So we configure, then we build, and then we do make install. And so these installed it on the scratch, my scratch space into gsmpio. So you can just go to a different direction. Does it work?
It worked for me.
Okay. So we can just go to that directory, my scratch slash gsmpio. So you should see installed files here. There should be a Grayscut executable, an ADIOS II XML file, and the settings files, JSON file. That's the application's own input file. Right, yeah. So you got it? And yeah, okay, so let's start. Let's run a one node interactive session. That salloc command here in the slides. That's how you launch a single node with 64 core allocation. And that's enough for our purpose. Okay, I got mine. So now I'm on a compute node. You have it?
I'm still trying.
Oh, you can, you're not
in the record. It's going back and forth, but I'm happy what's.
Oh yeah, it's copy. It's faster to just copy over the source.
I didn't think that one for me.
I'm happy to do one.
Okay.
Well, okay, so you have the slides and you have access to settings, so you should be. Maciej already ran through these PDFs to run through, and he could do it. So even outside of tutorial, you can do this. But the point is that you edit the source code and you learn the ADIOS codes and get reinforced. Okay, so now we are able to run the code, and that's srun. So in srun, sort of MPI run, right? Srun is to launch one executable. And what we say here is that we want to use 16 NPI ranks, and we want to use 16 on per node. And see, we have one node, so yeah.
Raise the window, make it not long, because for most people, see the bottom.
As you can clear,
It
probably the easiest thing.
would be okay. If you leave them.
maybe halfway or 3/4 away from, you know.
Is this okay?
Do a little bit
Also,
less.
Less?
A little bit.
why are you?
There you
Okay, you get it? You see it? Okay. What I'm running? No, it's not really the. We run this code, right? So we run whatever 16 MPI task. The settings files JSON, which will point to the ADIOS XML. But we don't use the ADIOS XML in this example, so that's so this is an MPI IO code, and it ran 1,000 iterations and output data every 10 iterations, so we have 100 output steps. So we have a file data.u. So we only output one variable, the u. The v is missing. It will be your homework if you want to learn MPI-IO to add another one. I'm suggesting not to do that.
Yeah.
So that's a nice binary file, and you trust me that it's correct, right?
Which one?
That it's correct. How do you look at it? The content.
Oh, okay.
That's
Right.
good.
I can tell you, but it's just for fun. You do OD. The first one. Well, actually, it's a 3D array, so we just need the first 24 bytes printed. It's the 64 cube data set. And then we have, well, it's 100 times. That's not written how many steps we have. It's just the file size. So the Python script is going to read these three 8-byte values. Okay, and it's 64. Then it checks the file size is 2, whatever. What's the size? 20 megabytes, something, right? So it will just calculate, okay, this must have 100 output steps of U. And then so it will loop over that and read the data, the 2D array. It's stored contiguously. That's what the MPI-IO code does. So it's very simple. So you have 8-byte values for describing the 3D space, and then you have that array written contiguously, step by step. And if you run the plotter, that's basically running a single process. It will read the middle slice, right?
The last one is the plotter.
Yeah.
Last one.
Yeah, it should. Okay. So the mistake is that the input file is called data.u. This is the comment, data.u. And so it said it's found 64 cube and found 100 steps, right? And now it's going to read the plots. Yours is faster? You have a better machine?
Yes. But you.
Huh? Oh, you run the PDF calc. Oh, that's a different application. You run PDF calc?
Yeah.
Oh, that's just in italics. That's not okay. So you are doing, yeah, that's a C++ code reading it, and this is a Python script reading and doing a plot in Matplotlib, which is 10 times slower. So, right. So the output, what you should see is 100 PNG files. And now, if you were careful and you logged in with X connection to Satonix, you could run events and then see your PNGs. I can't, because if I was hopping through Magnus and I don't have X on these working X connections from these Windows machines. So, is there a way that some of you can see PNGs?
While you're asking that question, I just want to quickly remind individuals to put their name against a training account that they're using so that another person doesn't inadvertently use the same account. Just a quick reminder. Thanks.
What was that? That was a response? Well, okay, so my images are on the PowerPoint, so it's easy for me to show. Well, if we could SCP to set on it, so Magnus, so yeah. We are a few hops away from looking at images. That's yeah, but I don't have a working Windows X server locally from this WSL into the Windows, and so I cannot do that. I could only do SCP, but then we have 2 hops to work through. Yeah, it's something that Microsoft couldn't do, but companies do. It works perfectly in my home computer of my life, not the Oakley.
Security reasons, I don't think it's very strange.
I don't know. I couldn't figure out how to do it, so that I don't know. I mean, everything, all the ports are closed, and if you don't find a guide on the web how to which one to do, I can figure out. It's called
No, but which logging node are you? Atomic 0, 1, 0. Well, I had the last time. But it should be there once it's on your page. If you type EV and tab. Yeah. Let me try. Let me do the check around with that.
Here. You got it.
Okay.
That messes the noise in there. Oh, from Galaxy you can see it. Yeah, okay. So, yeah, we are not giving a tutorial how to look at images produced on Saturn. That's Pawsey's problem. The show. Okay, so we have 1 hour. 1 hour left. So yeah, so can you show your image around just so trust him. Trust him that you have the same images.
This is number 10, why is it? I just copied from the PowerPoint slides, so is that okay?
So just to know, if you're on Satonic 03, it doesn't have events in. That specific log node.
So I will go out from here and let's start working.
So it's in the maintenance update that will be off. The images that are put in the log node will be updated. Currently, events the viewer for like pages and all this stuff. It is on 0, 1, 2. So if you get sent to 03, you're not going to be.
Okay.
Yeah.
So let's go and let's edit code. Let's look at it. So go back to your software directory and copy the GSMPIIO into a directory, whatever you call it. Just make a copy of the GSMPIIO source code. You can quit your job.
Oh, on the source.
Yeah, so you don't need your code. Just go back to the software, the source code. You can quit your interactive job because we are going to edit the code. We are not going to run for a long while, right? So go back to the source. In the tutorial, you have GSMPIIO, and then, well, the slide says copy it to my code. So we copy the build directory was not necessary, but anyway, so we have my code and no, that doesn't matter. Sure. Okay. And so first, just let's go through the CMake business.
What do you want us to delete? Sorry,
Do what?
what did you want us to delete? You say.
Oh, follow the slide.
Ah.
So when you get the MPIIO, you copy it, but the build is right now, we don't need it, or we start from scratch, right? But it's basically, so far it's the same code. So but CMake doesn't like changing passes, so you would need to reconfigure and rebuild anyway. So when you use ADIOS in a CMake project, and this is a C++ project, then what you need to look for is you need to do a find package, ADIOS II, and then it will set the targets for that. And when you have an executable, you want the links, then you use the specific targets. So we have ADIOS 2 : and then we have the API. This is a C++11 parallel version of the API. This is what we are using. You have XX11 for serial code. You have Fortran. You have C for different code projects, right? So these applications using MPI C library, not the MPI CXX, so has these strange things to avoid the MPI C++ API. No one is using that as far as we know, right? So everyone is using the C version. And so we just add these ADIOS target. And so now when it tries to link the Grayscale application together, it will add the necessary ADIOS libraries. And when it compiles, so this is add executable, Grayscale executable source code, you enumerate the source code, and it will generate the compile comments for every single source code. It will add the include pass, it will add all the packages that it found. And so we can include ADIOS because it will find it. And then when it links with the ADIOS libraries. That's all we need to do for us in the project.
Just a quick question on the ADIOS setup, right? Because you can also build ADIOS, like a version you could turn off BP5 for some reason, right? You could build an ADIOS. Does the CMake have the setup to put in requirements saying this is what I need to see from ADIOS? Is it?
Cool question, actually, I don't know.
Okay. I mean, remember last checking, but it was.
Yeah, I don't know, but yeah, so you cannot turn BP5 anymore. That you cannot turn it off anymore, BP5. But yeah, HDF5 is an optional thing.
Yeah.
Situ is an optional thing. So mguard is an optional thing. So yeah, there are optional stuff. And I actually, great question. I don't know the answer. If you could check that. No, this is already set up because I don't want to spend time with this. So let's go to the build and just do the same CMake command, right? We do CMake, but change the installation directory to something else, right? So it's called like scratch my code. My code is just for following the slides perfectly. Otherwise, you can call it whatever you want. And then the make will, of course, succeed. Now is the time for me to go to this different directory and just do these builds somewhere else. So if you have the luxury to have 2 terminals, that's useful. Here we are just going to edit the software. So far, we didn't do anything, just copied the code and build it again, just like before. So everyone succeeded? Yeah, so let's look at the code. So is the simulation directory, this is the Grayscale code, and there is a main.cpp. The Grayscale CPP contains all the calculation functions and the data pointers. The settings is to process this JSON file. You can just steal that if you never process JSON files. So it's a nice way to provide input files into a C++ project. And then writer.cpp is the class to write the data. So we only need to edit the main.cpp and the writer.cpp and header files for this IO. So if we look at that, basically the structure of main is a big loop. So there is only a big main function which will create, processes the settings from input, then creates the grayscale, sets up the simulation itself with every process allocating memory for its ghost cells and the data, and initialize it. And then we initialize the output writer. And then we just have the computational loop is here, for loop. This is the iteration loop. We go through all the iterations and do iterations for the plot gap. So this is set up to 10 steps, set up to 1000. So every 10 step, we are going to call the writer and write the data. And to do 1000 iterations, do 100 output steps, and then we close, finalize, and so just simple iteration loop. And the writer is the code that does all the I/O part. So when we create the writer, this is the constructor. When we create the writer in the beginning before we start the computations, what the MPI I/O code does, this is the MPI I/O code. It basically creates two MPI types to describe the memory with the ghost cells and to describe the 2D array, or the 2D, this is 3D, sorry, a three-dimensional distributed array of the processes that you want to see as a contiguous 3D array in a binary file. So there you see the twice, it repeats the code twice. One type is for the ghost cells, one is for the n-dimensional distributed array. Then there is the open call, which is called once. Again, what this does in MPI I/O is that we we open the file. So this is open. Basically, we open, and then rank 0 writes the header, which is the input dimensions. And in these grayscales we have a cube, so it's 3 times the same number. But anyway, we write the header, and it's 3 times 8-byte information. And then we set the view, MPI file view. This sets up MPI I/O so that we'll expect data from every single process, and then it will merge that data and reorganize it into a nice contiguous, logically contiguous 3D array that writes into the file. So this is set up in open, and then every step we call write. And in the write, this pointer, this vector reference is basically the data, the variable u, including the ghost cells. So this is reference, not a copy. So we are directly accessing the same object, the simulations data. And we just pass to MPI I/O with MPI file, right? We pass this data pointer and saying we are writing a single element. A single element is that 3D data content of the process within the allocation which has the ghost cells. So it will be like 32 cube on every process if we run 8 process. Also with 16, it will be 32 by 32 by 16, right? And then you have with the ghost cells, you have +2 in every dimension. So this is how you use MPI I/O. It's in the slides if you are interested to learn this. And so MPI I/O will reorganize it for you to have a nice, logically contiguous 64 cube data in the file. And so if you read that whole thing in, you have a nice memory piece easily. And then once we call close at the end, that's just close MPI file close, and we are done. Right? So it's simple structure, and that's what we want to change it to ADIOS. So how do we do this? The first thing to do it doesn't matter what is the first thing, but so first thing we do in the main, let's set up ADIOS, right? So first thing to do is include ADIOS as a library. Include ADIOS2.h. These steps are all in the slides, so if you get behind, you can just follow the slides and you should be able to do this on your own. Yes, Pascal?
So the trying to think of kind of keeping the writer sort of separate from any ADIOS declarations in the main. You could obviously just have it in the writer class where you can tell it to construct an ADIOS object and return it. So is there any particular reason?
Excellent question. We didn't get there, so you are a bit early. It's a great question.
Yeah.
But yeah. So particular reason is that we created this example from existing example, particularly for this tutorial, and it is how it was written. Yes, you can hide completely ADIOS somewhere else. You just need an ADIOS object. And if in a this would be the application, you have only a single output and you hide it in the writer class, you can put all the ADIOS objects there. You don't need to have it here. The main example that we use in tutorials also have a checkpointing. So they have two different outputs.
Yeah.
And so you have to decide what are the objects that you are going to pass down to subroutines or different classes to share it. And in this case, we share the IO class, IO object, right? So we create ADIOS object and IO object here.
Yeah.
But there is no particular reason for that. We could create the IO object in the writer constructor and just use it locally.
Yeah, I was just wondering if there's some deeper reason, because most of the examples I've seen, I've only done this. Hide it all away. But some of the examples I've seen, all the examples, I'm always taking the ADIOS thing and using passing the IO.
Yeah. So it does, but it's basically because I wrote those examples and I have my own style. That's the only reason. You put it very well. But you need to global access to pass it around, right? So that's the only reason. Excellent question. So let's do those lines there. So after initializing MPI, we will also initialize the IO, or actually initializing everything else. So here, we need to create first the ADIOS class, ADIOS2 object that we commonly call ADIOS, but it's kind of confusing, but anyway. And then we so we use ADIOS2 XML as typically is whatever is the name of the config file, and the com is the communicator, right? So this will create the ADIOS objects, and as I discussed with two of you, at very large scale, ADIOS is only reading these on a single process, and then will broadcast to everyone else. So it does scale, because even reading a very small input file on every single core is a bad idea at large scale. But that's just snippets of information. Okay, so I decided here to create an IO object. Not a requirement, but this is how we do it here. IO equals we have an ADIOS object and we call declare IO, right? We just keep a name. Anytime when you feel like it, go and try to build it. So far I didn't make any mistakes. So the make, you see the on the bottom, right? Anyway, so if you make a mistake, then you will get errors. And I know the one thing we have to do it is that in the writer we will pass down the IO object. So if that's so now I should get an error because obviously I passed down an extra argument to the function which doesn't have it. So that's points to that we need to edit the writer header, right? The writer class. And so basically we are done with the main. This is synchronization point. So show your hands if you are done. Okay. Are you going to do it? Okay, then we can move on. So now we can go to the simulation. So in the simulation, let's edit both the header and the C++ file. Yeah, so since unfortunately this application doesn't have a global header file, it has, so we have to include the ADIOS header here too. And we have an extra parameter to work with, which should not be const because we are going to change it. That's the ADIOS to IO object. Right. And now you have a decision to make. Do you do reference or copy? Want to hear questions about that? And then we in the class we need to create some. So obviously we pass in the IO, but we need to remember for the other classes if you don't want to always pass it. So either you pass down the IO object for every single function or you remember it. So that's what we are going to do here. You remember the IO object and yeah, okay, let's do that. And then I will just go as I develop it, right? So, so we have an IO object.
Is there a reason you wouldn't pass it by reference?
Sorry?
Is there a reason you wouldn't pass it by reference for the IO object?
Yeah, so that's an interesting snippet. So if you just decide always pass ADIOS object by reference, you are good.
Right, okay.
But the so ADIOS C++ API is on top of the ADIOS framework's own C++ API.
Yes.
So these objects are tiny. And they reference the real stuff behind it. So even if you pass down and you make copies of it, you don't pay a huge price.
Right, okay.
But this is just convenience.
So if it's a handle, why do you don't pass the const reference? So it will be copied, so you will still get the copy, which you can modify as long as you want.
And so the what?
So in the writer, why not to pass const reference? If you later create a copy to.
Because then the IO functions, some of them which changes the content of IO will refuse to compile. Huh?
But you will pass the local variable class.
Because you're actually having a local IO.
Yeah, so you create a copy in the constructor anyway.
Oh, but
If you basically you can pass the reference, non-const reference, and then non-const reference in the class member, or you pass
okay.
const.
So now you just got me that I'm a rookie in C++. I haven't been using it more than 10 years or whatever, so I'm rookie. So yeah, I'm not sure if that works. When I tried const, it didn't work, but yeah, I used const on both sides, and then that's why it didn't work.
Well, normally.
All right, okay, but yeah. Yeah, so you see that's up to you. There's nothing tricky here. It's just you need access to the IO objects in the writer.
Can generate
Or the HTML object handle copy.
Yeah, but that's something that very good to know, because I think you sure that people might be putting with don't the IO handle must be huge.
Yeah, I mean, so if you just pass handle, the rule is if you just pass handles and you make sure that this is what's happening, you are good and you are doing the right thing. If you make mistakes with passing by copy, you are not doing huge mistakes. That's basically the point of it. So, yeah, so let's back to the C++ code then. Right, so now we need to edit the writer and say, okay, we have an extra argument, which was, are you saying we should try const?
Well, I think we're not going to use handles all the time. in the local one, then it wouldn't matter.
Oh, you can do it response. Just we have to do it before spinning.
Yeah. So let's try that. I wonder how this is working. So I pass a const reference here, and then have an IO object that I make a copy. Let's see. So far, so good. Okay. So here we have comments just to describe what we have for the what we want to achieve. Right. So the first thing what we want to do is just write out the step, the iteration of the simulation as a value. Right. That's a global value, and we just want to see, okay, when the output step 30, which iteration was that? So for that to do, we just need an integer variable. So we call that var step, and then we say io.define variable. And basically we just give a name. I call it step, but you can call it iteration, whatever. This is the name of the variable that will be in the out. It's just the name that shows up for the consumer. So you name it the way it makes sense for you, or better yet, what your applications consortium decided as the schema for using. Okay. And that means if I try to build this now, of course, I don't have var steps, so I need to create this variable. So in the header file.
Yeah, so here there is I think that's the reason why you had issue with const non-const.
Yeah.
Because you access from the constructor under the same name, and it will use whatever you pass in the arguments.
So if I see. So if I just do my this,
that way.
okay.
So it's just make sure that the simplest thing is in the constructor when we're actually having there is just like underscore IO is the things that are going to get tossed away, and then IO construction with underscore IO.
Yeah, let's call it. Yeah,
Yeah,
we'll call it underscore. Okay. So what is the compiler returning?
Find variable one stins ones. Did you get to one? Yeah, did
Oh, okay.
Yeah.
Good catch. Good catch. Thank you. Thank you. As a funny tutorial, I'm going. That's what. Okay, so let's do the coding. So this is the easier part. So this is the first variable. The second one will be the describing the 3D space that's more involved. Okay, so let's define the 3D array, and that's similar what in the MPIO, and as I discussed, the first part of the defined variable is what you want to see in the output. So the global shape is the target 3D array, and then every process saying how much data they contribute in that output 3D array. So that offset and size is the actual data, how it's constructing the array, nothing to do with the ghost cell business. Okay, so that pieces of two pieces of information there. And there it's you can just copy paste because in the comments basically it's here the first you pass a name, then you pass the shape, and it's basically a vector of the settings L. It's a 3D cube. Then the second parameter is the starting offset for every process. That's again a 3D. No, it's a vector of 3 elements. And the size is the size Z, size Y, size X. Yeah, so you can see I didn't write the Grayscale simulation code. And you can see that whoever wrote it originally got some, the ZYX is more like a Fortran. Or some people who wrote the equations and whatever was in Fortran thinking, where Z was the slowest dimension, the third dimension, and whoever implemented this in C++ and kept it ZYX. So now Z is the slowest dimension, so it's the first one to make this properly work. It never makes any sense to me. If I flip it the other way, I never know what went wrong in the plotting, or it's just an interesting piece of thing. So I don't know, ZYX is always confusing. Let's see the application program and all this. We just follow for the IO now what we have to do. Okay, and so this is the first part information, and the second part has a separate function. The set memory selection is to describe this ghost cell business. So we pass the two extra information. One is that, okay, if you have a pointer in memory, then where does the actual data that you want to output start? And that's, we have one ghost cell in every direction. So it's 1 by 1, 1, 1. And then the one missing information, okay, what is the allocation size? Because from the pointer, we don't know how much, ADIOS doesn't know how big the pointer is. So you have to say, okay, my pointer is L plus 2, L plus, well, not L, but Z plus 2, Y plus 2 times X plus 2. So that's what we have to tell them. And for a particular peculiar reason, this should be passed as a pair instead of two inputs. It's just inconvenience, but so now we change the variable definition itself, right? So the variable itself has functions to change it. Set memory selection, and that basically is a pair, and then this is always a little bit involved. And the first element is the offset once, right? Yeah. And the second one is the size of the allocated memory. Let's see if that built. Okay, I got that.
Mismatch of complaining compile time, the fact that there's not enough arguments in the pair.
You mean this, not the 3 elements?
Yeah, if you don't specify.
At
Try,
run,
try.
no, at runtime it would.
At runtime, it's certainly.
Because, yeah, so these are just, yeah, it wouldn't know that this is a 3D variable. The compiler wouldn't know that it's a 3D variable.
Okay, so ADIOS doesn't complain that there's a mismatch with that.
No, ADIOS would, but ADIOS is not here. When you
Yeah.
run, ADIOS would complain that you only pass 2 values for a 3D array. But yeah,
And then give you a warning, right? I'll give you an error message that's useful.
I hope so.
You gonna try?
If it doesn't, then at least should be nicely abort on, no, it will be quietly corrupt your data.
Yeah.
The best thing, yeah. Okay, so and one more just for to define attribute. That's so easy, but it's underappreciated. Try to do this in any other IO libraries simply and easily. So you just say, okay, one of the input arguments, the F, is a double, and we just want to save this for record. Okay. And that's all what you need for the attributes. You don't need to worry about this anymore. It will just show up in the output. Right. Okay, and then all we need to do is remove the MPI IO code from here. Okay, time is okay. Good. Show your hands if you have it. So basically, this is definition phase, right? We didn't do any IO. We didn't open anything for output. This is just we defined it when the constructor was saying, and we know that this application has variable u and v. It will be your homework to add the second variable v, and this will be really homework. It should be very easy. Right? You don't need to deal with offset, so it should be very easy. Okay, so now when we go to open, delete this code because nothing tells us to do here. So you just delete the entire write open. And what we do here is, let's say we have the IO object open and we created an engine object, which is writer equals IO.open. And now we need to give a name, which was fname. We also need to say that we are doing open, write mode. So that's for open, and then for close, you just do writer dot close. And as you see, we do open in IO and we close writer. That's because constructors and this construct is different. Okay, and then when we do print settings, that's just crazy. Anyway, so when we write, okay, when we write, we don't do the MPI IO stuff. Instead, this is what the longer than what the MPI IO code is. We need to do a begin step, end step pair, and in between we should pass the pointers for the IO, right? So this is the meat of the whole IO code. So writer begin step. Step. And in between we will pass the pointers. So that's a put. I don't think we need the type here. Just do put, and we have the var u, and we pass the u data pointer. We don't have a communicator, so we don't know which one is rank 0. So we also do writer.put for step. And So this is the easy and lazy way of writing that. Now let's build the code. Just one more thing in the print settings. Yeah, there's just curiosity. We can instead of we can ask the engine. Is that here? Not here. No. I think it's the IO engine type function or the writer engine type. Let's see. Yeah, IO engine type. It will tell you which was opened actually. So because if you just use the default one, you don't know what engine you are using. So this is not on the slides, I guess.
So what is the type of writer? So I didn't have on my page file. So is it?
Oh, it's ADIOS II engine. This one? Okay. Build, install, and then hands in the air and run your job allocation again. Make install. Make install. This should be in iCode now. Oh, and run the job as Allah. Is your job starting? Did you get your job? Because this one is, it says ready, but it's not. Okay. One more thing to change in the setting files JSON. And look at the slides. It just changed the output from data to GS to BP. That's not required. It's whatever the file name you want to see. You just use BP as the convention so that you know it's a BP file. You can name it. Of course, whatever you want. So please run it. It looks like I'm not getting my job started up, so that let me know if you could run it.
It's ready.
Yeah, it says ready, but I don't know why. But where is it?
Sure.
It's initializing that mode, I guess, and somewhere it happens sometimes.
Yeah. Control C, try it again. Give you maybe a different penalty. Control C, do it again. It's not that node.
My experience. Huh? Scott, I tried that. I had this experience with it, and Control C leads with exiting Setonix and logging again and hope for the best, and it's just getting worse and worse. Yeah. So far, I can Control C, but because this doesn't seem to work, but then just can hope for the best. Well, okay. Not even Control C.
Control Z.
No.
I'm pretty sure this node is it's a node. Since it's in the state someone's using the node, right? Not all of them.
Oh.
It's quite possible that someone else is killed the node. I don't know. It's
Well, that's what I was thinking. That's why I wanted to get out of this.
Well, yeah, but now I need my terminal. Then, so.
Right.
What is it? Exascale?
Yeah.
Yeah, so I still have it. Time for a new terminal. And
if you have handy, some plans. And cancel.
Oh, it says cancel, not either. Okay.
There we go. What does it say?
I'll set the worded, waiting a couple of seconds to finish.
30, up to 32 cents. So precise.
The message is precise. Let's see if it's 32 seconds or not.
Wait, not 32.
It's up for time, but things. Yeah, no, Jones, it's.
Yeah, okay, but so the point is you did run. Who did run? Okay, so you have successful runs. Okay, so now I can try again. It shouldn't be because
There you go.
the visual, no, how? Yeah, but we didn't change the GFC. It's an MP, it's just treating an MPI IO file, so it's not.
If you want to write to HDF5, you simply specify the HDF5 in the output in the settings. You have to change the engine.
Not the settings, so the settings file JSON just says use ADIOS to XML for the ADIOS runtime parameters, so it's not in the JSON file. And then we never looked at the ADIOS XML, so now maybe this is time for it. So this IO here describes that the simulation output. So you see, that's why we use the IO declaration simulation output. So whatever is written here belongs to that runtime option. And use this file stream. This is just we call it virtual engine. It's just a name that provides a stream over file, and that's basically BP4. The default engine is BP4, but the file stream is the same thing right now. And what it changes is for that it's if you, on the read side, if you try to open a file stream, by default it will wait for an hour. If it doesn't exist, it doesn't just throw an error, it will wait because it's a file stream and hoping that someone will, it has a timeout. You can set the timeout, so it will only wait for 10 seconds.
And then it just errors.
And then you get an error. Yeah, so the answering the question is that you choose what engine you want to run, right, at runtime. This is where you can say, I want to use the ADIOS engine. So there is an...
It's at defaults as well. Right? When you construct the engine.
Well, I'm sorry, we don't have a name default. What?
No. But I'm saying, like, you could in the construction of the engine, you can specify when you have that writer construction to say when you're open, you have you specify a name, but you could also then set that writer to have sort of defaults set values, right, for the engine.
You mean in the source code?
In the source code, so that if it's not provided, this is what it will default to. Or should you let ADIOS always decide those?
No, but so there's the thing. So you call IO set engine.
Yeah.
Then say this is my engine.
Yeah.
But that comes after ADIOS initializing from this one.
Yeah.
So that's not the default one. That's the final choice.
Right.
So there is no way to set a default in code. Then use these XML if it's there and get.
Well, I'm thinking more like if you load if the XML is there. So if you don't have an XML file, ask the configuration file. Can you ask ADIOS, have you been passing configuration files?
Yes.
Right. So
yes,
then
if you remember, there was checkpoint example and then the analysis example, and it was the begin step and step. Before that, there is some code that I just jumped over, and that was saying in config file, a function to check if this IO that I just declared, is it in the XML? And if it's not, then you can set yours. So that is a way to do that.
I don't remember meeting for specify default.
So answer the chat question. This is you just change HDF5, and then we better change the name, the output to data.h5. Right? And so now if I run, actually I didn't run it before. Okay. We run the Gray Scott, we run this executable, and then basically what we see in the beginning, the engine type is HDF5, output data.h5, right? And if we look at the what file is this data.h5 is HDF5 data, right? So now you have to use h5 ls if I have it.
Should we go up on it?
Yeah, but
I mean, after.
right. So this is an HDF5 file, and use your tools, but you can also use the ADIOS DP. So for steps, it's basically specific is that HDF5, we don't use extendable dimensions because that's very unreliable in my experience. Eventually it aborts. So we are forced to.
This groups, right? And
Yeah, so I just create a new group. No, not I. We create a new group for every step and then just add all the variables in there. So it's very specific how ADIOS writes using HDF5 APIs to construct an HDF5 file. We are not binary. We use the HDF5 API to write HDF5 file. We are not having going around the API.
Yeah.
This is how we represent, and then ADIOS itself will process the steps and represent it to you. Oh, everything is the same dimension. You have 100 steps of a 64 cube array.
Remember, you have 5 or 8 minutes.
I know. Yeah.
Unfortunately, we didn't get through reading.
Yeah, but we have an entire 4 hour tomorrow. So this is where we end today. Now you have the simulation working properly. And even if you cannot join tomorrow, the PDFs continues, the slides continues, and it shows how to change the Python script to read. And you can do it on your own. And then you can also look at in the source directory. Oh, okay, I'm in the job right now. So in the source code, right, the tutorial has the GS ADIOS 2. This is the version that we are aiming to create. And so the PDF calc, there is the PDF calculation C++ code there, and the PDF plot Python code as well, which is an MPI-based parallel code in Python. So on your own, you can also go here and see those code examples to round the whole experience.
What might be useful, I know it's not exactly as planned, but there's things about writing at scale, and maybe since you have like 5 minutes, you mention a few of those.
Yeah, so let's end the hands-on here and have a half an hour presentation on scaling. So we can start it today on talking quickly, and then tomorrow we can go again.
So, I mean, one of the points with ADIOS is always like, we talk at scale. And sometimes people don't understand what it means to be at scale. And seriously, what does at scale mean? Does it mean lots of processors, lots of data, lots of variables, lots of time steps? Scale is on all those dimensions, and this has always, been a part of the research that we've been putting in production. So go ahead, Norbert.
Yes, so basically there is no source coding trick to improve this for large scale. Yeah, well, so you could just publish the step variable on rank 0 instead of every single process. It's not going to make such a big difference. But to make it, if you have a global value, you can just write it on a single process instead of publish it every process.
Yeah.
But otherwise, there is not much things to do there. The performance is basically depends, as Scott asked the question, how many subfiles you want to produce. So we didn't get, if you run the ADIOS example, you see that the gs.bp, the output file, is a directory, and there are a couple of files. And we see one data file in this example, because we run on a single node. Whatever number of processes you wrote, the default setup is 1 file per node, which is not a good default because it's underperforming when you run on 100 nodes. It's not performing very well when you run on 10,000 nodes, but you don't have 10,000 nodes. But the good number is two or three or maybe 4 times the number of OSTs of a raster file system. And it's really, you have to figure out on the actual file system you are using, is it 2 or 3 or 4 the best? But so aiming for that number is to get the highest bandwidth on a file system. And that's what we have the aggregation for.
So that's also assuming that you are not competing with anybody during the OST. So I'm wondering.
That's always the case. Yeah.
Yeah. So,
And that was the slides on the variability,
yeah.
which is very much influenced by the other users doing stuff.
There's no way though, I mean, until, I mean, that's part, until we get this rerouting.
Yeah.
In production, which, I mean, again, it's one of the many on the list.
Yeah.
You're best off to do this, because how do you know which ones people are on and which ones are not?
Yeah.
Especially if you have a 10-hour or 20, it's transient.
Yeah.
So you go for all of them. In general, you'll get the best. And that's why we really need this other thing.
Right. Okay.
I just can't get people to do it.
Yeah.
Yeah. Okay.
So anyway, so since we have what? Yeah, 3 minutes. So there are 2 things to work with. One is this aggregation. Absolutely, the aggregation is the main thing. Any application you take and you try this scaling, if you do it yourself, you get the same result as what we do. Is that when you run at small scale, the best choice is to create one file per process. POSIX IO, right?
Yeah.
Everyone just writing this in Fortran IO is to create. So this is Summit 42 cores, 42 MPI tasks per node on a single node. Actually, this was 42 nodes, so 42 by 42. It's a lot, right? Parts of that, but 1600 something, but it still gives you the best performance. And if you choose a single file per node, it's not so good. I mean, this is a good number for a lot of applications. So the default is not stellar for small, medium-sized applications. You could use more subfiles. But as you start growing up, all of these start breaking down, right? And so, at this scale, the best one would be the 6 writer per node. No, sorry, yeah, this was 6 files. And we have 6 GPUs, 6 MPI. That's usually the GPU was running in, and we have one file per GPU was here, but this was only 336 nodes. We have 4,000 something nodes, right? So the 1 file per node is the one that you can expect to fare well until even you exceed. If you have lots of nodes and less OSTs, then at some point you would have to say 1 file per 2 nodes would be the best. So this clearly the number one thing that you have to focus on. Not 1 file, not n files, but somewhere in between related to the number of stories, to the capability of the file system. The consequence of this is that if you do have 1,000 output steps, one output step has hundreds or a few thousand files. And 1,000 steps, you create new data sets, then you have millions of files on the system. That also starts to stress the system. So the ADIOS Open is more costly than NetCDF Open or HDF5 Open because they only create a single file and you create a directory with data files in there. So you pay a cost at Open. And at large scale, this is going to count. And so the second step, moving on, getting good performance, is to have the same output data set and append multiple steps in there. So for ADIOS, writing the steps into the same output data set is important. For others, it's not safe. So no one has been doing that because they don't trust that in the 24-hour runs, application crashes, your data gets corrupted, you lose the entire data. In ADIOS, as we stated many times, the output steps go out, and if you get
another step being constructed and written halfway and things go bad and crashes, it does not corrupt your previous data and you can still access it up to that point. So it is safe to use for the entire run with just open once in the beginning and then always write to the center. And in this way, you amortize the cost of the large open.
The only comment on that one is, what's also good about it is then if you're going to do staging, then it just will work.
Well, that's of course staging required that you have one stream
Right.
of multiple steps. So that was the other one. So it's basically this one shows on. Create a little bit. If you don't do that, then basically you have initialized startup cost of creating an office for the entire. So these are the two things basically to discuss in 5 minutes. That is not, yeah. This is what the applications do together.
But that's,
They don't do other things.
but that's the thing that we keep trying to say with ADIOS. It's like, at scale, there's not really tricks. There's like just a few things.
Yeah.
I mean,
So that's a
Go
bit.
back to the BD comparisons.
Which one?
Yeah, BD4, BD5. Size.
Yeah, you called this one.
Yeah.
Yeah, okay, so. Okay, it's after, please, this is not, after we are done here,
Yeah,
lunch discussion.
okay.
It's not showing what you expect, and so I need the explanation, whatever. So I made a mistake to show it to you right now. You don't need it right now. So these are the two things: aggregation, choose it carefully, and write a single stream of steps instead of creating new data steps every time.
that's why I say SEP would be interesting. Because now it's different. Like Lustre and GPFS are not that different. There's certain things which reasons why people like Lustre. Like I like Lustre because I can do the space phone curve. I can't do that on GPFS. I like Lustre because again, I have control. The problem is a lot of facilities don't like Lustre because then people do certain things. And they want to limit the scientists from doing certain things. So it's good for like middleware developers. And when you let scientists do whatever they want, they generally do the bad thing. Like they try to write one file and they scrape across like one.
Yeah. Hopefully the PFL that we've got alleviate that. Didn't have it very long.
Sure.
So
Yeah.
we are done for, well, okay, so we are done for today. Your homework, there should be a homework, right? So that we have stuff to check yet tomorrow. So what is the homework?
Want to put the other variable E,
Exactly.
which could be really simple. Should take you less than 10 minutes.
You only pass here, yeah. Right. And then you can compare it with, if you try to do this with MPIIO and see how, but the point is, it would be really the point when you have the Python plotter, changing your reader to work properly when you add something to a binary file is a nightmare. But with ADIOS, it's pretty easy. So yes, thank you, Anne. So we are done. It's really just, if anyone has last questions.
So to everyone online and in the room, I'd like to thank you for attending, and
On the obvious part, probably you can
we
fix
will
it.
see you tomorrow.
Again, in